Welcome to the gentle world of COBOL coding, where learning meets relaxation. Find a cozy spot, let your body sink into comfort, and allow the soft rhythm of this tutorial to guide you. Close your eyes if you like, and let the words flow like a lullaby. This is your space to unwind, to explore, to dream in code. Remember to like and subscribe for more soothing lessons that turn complexity into calm. Let the journey begin. Good day. Today's session will explore the COBOL programming language, a foundational tool in the world of software development. We will begin by defining COBOL and its historical significance, which dates back to the late 1950s. This training course is designed to equip you with the knowledge to understand and work with COBOL, particularly in the context of legacy systems and enterprise applications. By the end of this session, you will have a clear understanding of the key topics we will cover, including COBOL's structure, components, and its role in modern computing. While COBOL may seem dated, its relevance persists in industries such as banking and government, where it continues to power critical systems. Let us begin by delving into what COBOL actually is. COBOL stands for Common Business-Oriented Language, a name that reflects its original purpose. Developed to address the needs of business and administrative systems, COBOL was designed with readability in mind, making it accessible to non-technical users. This emphasis on clarity set it apart from other programming languages of its time, which often prioritized conciseness over human readability. Today, COBOL remains widely used in legacy systems, particularly in sectors where stability and reliability are paramount. Its ability to handle complex data processing tasks has ensured its longevity, even as newer languages have emerged. Understanding COBOL is essential for anyone interested in the evolution of programming or the maintenance of critical infrastructure. The origins of COBOL trace back to 1959, when the Conference on Data Systems Languages, or CODASYL, was formed to create a universal programming language for business applications. This initiative led to the development of COBOL, which quickly became the dominant language for mainframe computing during the 1960s and 1980s. Its widespread adoption was driven by its ability to manage large-scale data processing, making it a cornerstone of early enterprise computing. Even today, COBOL is critical for maintaining legacy systems in fields such as banking, healthcare, and government. Modern adaptations of COBOL, including integration with contemporary tools and cloud environments, ensure its continued relevance. This blend of historical significance and modern adaptability makes COBOL a fascinating subject for study. A COBOL program is structured into 4 main divisions: identification, environment, data, and procedure. The identification division contains metadata about the program, such as its name. The environment division specifies the system's hardware and software requirements, ensuring compatibility. The data division defines the variables and data structures used throughout the program, while the procedure division contains the executable logic. Within these divisions, sections such as program ID and working storage provide further organization. COBOL's syntax is intentionally verbose, prioritizing clarity over brevity. This design choice enhances readability, making it easier for developers to maintain and modify programs over time. Proper use of comments and indentation is also crucial for fostering collaboration and reducing errors. The data division in COBOL is responsible for defining the variables and data structures that the program will use. This includes both elementary data types, such as numbers and characters, and complex structures like tables and records. The procedure division, on the other hand, contains the actual instructions that the computer will execute. It is here that operations such as calculations, data manipulation, and decision-making take place. COBOL's file handling capabilities allow programs to interact with external data sources, such as databases and flat files, making it well-suited for data-intensive applications. Control structures like if statements, perform loops, and conditional logic enable programs to make decisions and repeat tasks, providing flexibility in problem solving. Together, these components form the backbone of COBOL's functionality. Let us examine a simple COBOL program. The first line, identification division, marks the beginning of the program and includes the program name. The program ID line specifies the unique identifier for the program, in this case, hello. The procedure division indicates where the executable code begins. The display statement outputs the text, hello, COBOL, to the screen, while the stop run statement terminates the program. This example, though basic, illustrates the fundamental structure of a COBOL program. Each Each line serves a specific purpose, and the overall format emphasizes clarity and organization. As we progress, you will see how these elements can be expanded to handle more complex tasks. COBOL offers several advantages that have contributed to its enduring popularity. Its high readability makes it easier to maintain and modify, which is particularly valuable in large-scale systems. The language excels at data processing, with robust support for handling large data sets and complex file operations. COBOL's portability allows it to run on a variety of platforms, from mainframes to modern cloud environments. Additionally, the vast existing codebase of COBOL programs means that it remains a critical skill for maintaining and updating legacy systems. These strengths make COBOL an essential tool for professionals working in industries that rely on stable, long-term software solutions. Despite its strengths, COBOL presents several challenges. Its verbose syntax, while beneficial for readability, can make programs longer and more cumbersome to write compared to modern languages. Integration with web and mobile technologies is limited, requiring additional tools or middleware to bridge the gap. The pool of developers with COBOL expertise is shrinking, creating a skills gap that many organizations must address. Furthermore, specialized tools are often necessary for modern development practices, such as version control and testing. These challenges highlight the need for ongoing training and adaptation, ensuring that COBOL can continue to serve its purpose in an evolving technological landscape. In conclusion, COBOL remains a vital component of many enterprise systems, even as newer technologies emerge. Its historical significance and continued use in critical industries underscore its importance. By understanding COBOL, you gain insight into the foundations of software development and the infrastructure that supports modern businesses. This session has provided a foundation for further exploration, including writing and debugging COBOL programs in the next session. As we wrap up, remember that while COBOL may be an older language, its relevance endures, and mastering it can open doors to unique opportunities in the field of programming. To begin your journey with COBOL programming, it is essential to gather the necessary tools that will support your development process. These include a COBOL compiler, which translates your code into executable format, an integrated development environment, or IDE, which provides a structured workspace for writing and managing code, and a text editor, which allows for manual coding and file management. Before proceeding, confirm that your operating system, whether it be Windows, Linux, or Mac OS, is compatible with the tools you intend to use. This ensures smooth installation and operation. Additionally, ensure you have a foundational understanding of programming concepts such as variables, loops, and data structures, as these will aid in comprehending COBOL's syntax and logic. Lastly, make sure you have access to a terminal or command prompt, as this will be necessary for executing compiler commands and testing your programs. Installing the COBOL compiler is a critical first step in setting up your environment. Begin by downloading a suitable compiler for your operating system. For Linux and Mac OS users, New COBOL is a popular choice, while Windows users may opt for Open COBOL. Follow the installation instructions provided by the compiler's documentation, which typically involve downloading the software, running an installer, or compiling from source code. Once installed, verify the successful setup by checking the compiler's version. This can be done by opening a terminal or command prompt and typing a command such as COBOL version. The output should display the installed version number, confirming that the compiler is correctly installed and accessible. This step is vital to ensure that subsequent commands will function as expected. Configuring environment variables is another crucial step that allows your system to recognize and use the COBOL compiler. The path environment variable directs the operating system to locate executable files. To set this, add the directory where the COBOL compiler is installed to the path variable. On Linux and Mac OS, this is typically done using the export path command, while on Windows, the set path command is used. After modifying the path, test the configuration by opening a new terminal or command prompt window and entering a COBOL command, such as COBOL. If the system responds with the compiler's usage instructions, the configuration is successful. This step ensures that you can run COBOL commands from any directory without specifying the full path to the compiler. Choosing the right IDE or text editor can significantly enhance your productivity when working with COBOL. For a more robust experience, consider using an IDE like Eclipse with a COBOL plugin, which offers features such as code navigation, debugging tools, and project management. Alternatively, Visual Studio Code with COBOL extensions provides a lightweight yet powerful environment with syntax highlighting and intelligent code suggestions. Install the necessary plugins or extensions for your chosen editor, ensuring that they are compatible with your operating system. Once installed, configure the IDE to use the COBOL compiler you previously installed. This involves specifying the compiler's location and any additional settings required for the IDE to interact with the compiler effectively. A well-configured IDE streamlines the development process and reduces the likelihood of errors. Creating a sample COBOL project is an excellent way to test your setup and familiarize yourself with the language. Start by creating a new directory on your computer to store your COBOL files. This directory will serve as the project folder. Next, open a text editor or IDE and create a new file with the CBL extension, which is the standard file type for COBOL programs. Write a simple Hello World program, which is a common introductory example. This program will output the text Hello World to the console. Once the code is written, compile it using the command cobx hello cbl. The X flag tells the compiler to generate an executable file. This step converts your human-readable code into a format that the computer can execute. Testing your COBOL environment is the next step after creating and compiling a sample program. Run the compiled executable file to verify that it functions as expected. If the program outputs Hello World without any issues, your environment is correctly configured. However, if errors occur during compilation or execution, carefully review the error messages provided by the compiler or runtime system. These messages often indicate the location and nature of the problem, such as syntax errors or missing dependencies. Troubleshoot these issues by checking your code for typos, ensuring all required tools are installed, and consulting documentation or online resources for guidance. This process helps identify and resolve problems before moving on to more complex projects. During the setup process, you may encounter common issues that require troubleshooting. One such issue is a missing compiler, which can occur if the installation was incomplete or the path variable was not configured correctly. To resolve this, reinstall the compiler or update your system's path to include the compiler's directory. Another Another frequent problem is path errors, where the system cannot locate the compiler due to incorrect environment variable settings. Double-check your path configuration and ensure it points to the correct directory. Syntax errors in your COBOL code can also arise, often due to incorrect formatting or missing keywords. Use the IDE's linter or the compiler's diagnostic tools to identify and correct these issues. By addressing these common problems, you can maintain a stable and functional COBOL development environment. A properly configured COBOL environment is the foundation of effective programming. It ensures that all tools and settings work seamlessly together, allowing you to focus on writing and testing code without interruptions. Before beginning any development, verify that each component compiler, IDE, and environment variables is functioning correctly. This includes checking for updates to the compiler and IDE, as newer versions often include improvements and bug fixes. Additionally, refer to official documentation and community resources for advanced configurations and best practices. By maintaining a well-organized setup and staying informed about updates, you can enhance your productivity and overcome challenges more efficiently as you progress in your COBOL programming journey. COBOL syntax defines the rules for writing valid programs. It is the foundation upon which all COBOL code is built, ensuring that instructions are structured in a way that the compiler can interpret and execute. The structure of a COBOL program includes divisions, paragraphs, and statements, each serving a specific purpose. Divisions are the primary sections of a program, such as the identification, data, and procedure divisions. Paragraphs are logical blocks of code within the procedure division, and statements are the individual commands that perform actions. Emphasizing readability and consistency is crucial in COBOL because programs are often maintained by multiple developers over long periods. A well-structured program with clear syntax allows for easier debugging, updates, and collaboration. The key components of COBOL programs are the identification division, which names the program, the data division, which declares all data items, and the procedure division, which contains the executable logic. These divisions work together to create a program that is both functional and maintainable. The structure of a COBOL program is organized into several divisions, each with a specific role. The identification division is the first section and is used to name the program. This division typically includes the program ID clause, which assigns a unique identifier to the program. The data division is where all data items and files are declared. This includes variables, constants, and file structures, which are essential for storing and manipulating information during program execution. The procedure division contains the executable instructions that dictate the program's behavior. It is here that the logic of the program is written, using statements like move, ADD, or display. In addition to these core divisions, there are optional sections such as the environment and configuration divisions. The environment division provides information about the system where the program will run, while the configuration division allows for customization of the program's execution environment. Understanding these divisions is essential for building a complete and functional COBOL program. COBOL programs are divided into specific sections known as divisions, each with its own responsibilities. The identification division is the starting point and includes the program ID clause, which defines the program's name. This name is critical for linking and referencing the program within larger systems. The data division is where all data elements are declared. Within this division, the working storage section is used to hold temporary data that is not part of a file, while the linkage section is used to store data that is passed from other programs or external sources. The procedure division is where the actual logic of the program is written. It uses paragraphs and sections to organize code, and it includes the begin and end clauses to mark the start and end of the program's execution. These divisions work in tandem to ensure that data is properly managed and that the program's logic is clearly defined. Mastery of these divisions is fundamental to writing effective COBOL code. COBOL syntax includes several key elements that form the building blocks of a program. Literals are fixed values that are directly used in the code, such as the string hello or the number 123. These are often used for constants or static data. Variables, on the other hand, are named storage locations that can hold different values during program execution. For example, a variable like WSName might store a user's name. Statements are the commands that perform actions, such as move to transfer data, ADD to perform arithmetic, or display to output information. These statements are the core of the program's logic. Comments are also an important part of COBOL syntax, beginning with an asterisk. They are used to document the code, explaining its purpose, or providing context for future developers. Proper use of comments enhances the readability and maintainability of the program, making it easier for others to understand and modify. The data division in COBOL is responsible for declaring all data items used in the program. Level numbers define the hierarchy of data, with 1 being the top-level item, 5 being a subordinate to 1, and 77 used for standalone data items. These level numbers help organize data into a structured format, making it easier to manage and access. Data types in COBOL include alphanumeric X for characters, numeric 9 for digits, and more complex types defined using picture clauses. For example, pic X10 specifies a 10-character alphanumeric field, while pic 95 represents a 5-digit numeric field. The data division also includes file sections, such as the FD file description clause, which defines the structure of a file. Record structures are declared using 1-level numbers, allowing the program to read from and write to files efficiently. Understanding these elements is essential for properly defining and managing data in COBOL programs. The procedure division in COBOL is where the program's logic is implemented. It is divided into paragraphs, which are logical blocks of code that perform specific tasks. For example, a paragraph named main logic might handle the primary operations of the program. Sections are groups of paragraphs that can be referenced together, allowing for modular programming. This structure helps organize code and makes it easier to manage large programs. The procedure division contains statements that execute actions, such as perform to call a paragraph, if to make decisions, or accept to receive input. These statements are the instructions that drive the program's behavior. Proper organization of paragraphs and sections ensures that the code is readable and maintainable, allowing developers to quickly locate and modify specific parts of the program. This division is the heart of COBOL programming, as it defines how the program interacts with data and performs tasks. COBOL programs use a variety of statements to perform actions, each with a specific purpose. The move statement transfers data between variables, such as moving the contents of one field to another. The ADD statement performs arithmetic addition, combining two or more numeric values. The display statement outputs data to the screen, making it visible to the user. The accept statement is used to input data from the user, allowing the program to interact with external sources. Finally, the perform statement executes a paragraph or section, enabling the program to reuse code blocks efficiently. These statements are the fundamental tools for building functional COBOL programs. Understanding how to use them correctly is essential for writing effective code. Each statement plays a role in the program's logic, and their proper application ensures that the program operates as intended. Proper indentation and formatting are critical for creating readable and maintainable COBOL code. In COBOL, statements typically start in column 8 or later, while comments are placed in column 7. This fixed format ensures that the code is structured consistently, making it easier to read and understand. Avoiding trailing spaces is important, as they can cause errors or confusion in the program. Aligning code elements, such as variables and statements, enhances clarity and makes the program's logic more apparent. For example, aligning the move statement with its operands improves readability. These formatting practices are not just aesthetic, they contribute to the overall quality of the code. By adhering to these standards, developers can create programs that are easier to debug, modify, and collaborate on, ensuring long-term maintainability. Mastering COBOL syntax and structure is essential for creating efficient and reliable programs. The proper use of divisions ensures that the program is organized logically, with each section serving a distinct purpose. The data division handles data declarations, while the procedure division manages the program's logic. Consistent formatting and clear syntax make the code easier to read, which is vital for maintenance and collaboration. By following best practices in indentation, comments, and structure, developers can avoid common errors and improve the overall quality of their work. Practicing by writing simple programs reinforces these concepts, allowing students to apply their knowledge in real-world scenarios. As with any programming language, experience and repetition are key to becoming proficient in COBOL. By focusing on these fundamentals, learners can build a strong foundation for more advanced programming tasks. Data types in COBOL are essential because they determine the kind of information a variable can store. This influences how the program handles and processes data. COBOL offers three main categories of data types: numeric, alphanumeric, and special. Numeric data types, such as PIC9, are used for numbers without letters. Alphanumeric types, like PIC-X, can hold both letters and numbers. Special data types are designed for specific scenarios, such as handling very large numbers or formatting outputs. Choosing the correct data type ensures that the program uses memory efficiently and performs calculations accurately, which is vital for maintaining data integrity and system performance. Numeric data types in COBOL are critical for handling numerical values. The PIC9 clause defines a single digit, and when combined with a number in parentheses, it specifies the total number of digits. For example, PIC95 represents a 5-digit number. The S in PIC-S9 indicates a signed numeric value, allowing both positive and negative numbers, such as S93 for 3-digit numbers ranging from -999 to +999. The Z in PIC-Z allows for optional leading zeros, which is useful for formatting outputs like zip codes or identification numbers. The V in PIC-V is used to imply a decimal point, such as 99V99, which represents 99.99. These numeric data types are fundamental for financial calculations, scientific computations, and any scenario requiring precise numerical handling. Alphanumeric data types in COBOL are used to store text and mixed data. PIC-X is the most common, allowing any character, including letters, numbers, and symbols. For example, PIC-X10 creates a field that can hold exactly 10 characters. PIC-A is reserved for alphabetic data, ensuring only letters are stored, which is useful for names or codes that must not include numbers. PIC-N is unique because it stores numeric data as characters, such as the string 123 instead of the integer 123. This is often used in situations where the data needs to be displayed or processed as text, but represents numerical values. While PIC9 is also used for numeric data, it differs from PIC-N in that it stores actual numbers rather than character representations. Special data types in COBOL are designed for specific use cases that go beyond standard numeric or alphanumeric definitions. For instance, pick 9,999,999,999 is used for very large numeric values, such as account numbers or identifiers requiring 10 digits. The C in pick CCCCCCCCCC allows for numeric data with optional leading zeros, which is helpful for formatting outputs like currency or codes. Decimal numbers can be represented using pick 9,999,999.99, where the period indicates the decimal point. Finally, pick 9,999,990,990. 9 is used for negative numbers with hyphens, such as in financial records, where negative balances are displayed with a hyphen. These special types provide flexibility for handling complex data requirements in real-world applications. In COBOL, variables are declared in the data division, which is the section responsible for defining the structure of data used in the program. Elementary variables, such as one name pick x20, represent single data items and are the building blocks of the program. Group variables, like one customer info, are collections of elementary variables, allowing for organized storage of related data. For example, a group variable might include fields for a customer's name, address, and phone number. This distinction between elementary and group variables helps in managing data hierarchically, making the program easier to read, maintain, and debug. Defining variables in COBOL requires the use of the pick clause, which specifies the data type and size. For example, one EMPNO pick 95 creates a 5-digit numeric field for an employee number, while one EMPNAME pick X 30 holds up to 30 characters for a name. The usage clause further customizes how data is stored in memory. For instance, usage comp stores numeric values in binary format, which is faster for arithmetic operations. Usage comp 3 stores numeric values in packed decimal format, which is efficient for decimal calculations. These clauses allow programmers to optimize memory usage and performance based on the specific needs of the application. The scope and lifetime of variables in COBOL determine where and how long a variable is accessible. Local variables, defined within procedures or paragraphs, are only visible within that specific section of the program, preventing unintended modifications. Global variables declared in the data division are accessible throughout the entire program, making them useful for data that needs to be shared across different parts of the code. Properly managing variable scope helps avoid conflicts, improves code readability, and ensures that data is used correctly. For example, a global variable might store a configuration value, while a local variable might handle temporary calculations within a specific routine. Understanding data types and variables is fundamental to writing effective COBOL programs. The right data type ensures that the program handles data accurately and uses memory efficiently, which is critical for performance. Variables, whether local or global, must be defined with care to maintain clarity and prevent errors. By mastering these concepts, programmers can create robust, scalable, and maintainable code. Whether working on financial systems, data processing applications, or legacy software, a solid grasp of data types and variable management is essential for success in COBOL programming. Literals are fixed values that are directly used in COBOL programs without requiring a variable. They serve as immediate data inputs, outputs, or components in calculations. There are two primary types of literals: numeric literals, which represent numbers, and string literals, which hold text. For example, numeric literals can be integers like 123 or decimal numbers like 45.67, while string literals are enclosed in quotes and can include characters, spaces, and symbols such as hello or world. These literals are essential for providing direct values in statements like display or arithmetic operations, making them a fundamental part of COBOL programming. Numeric literals in COBOL represent numerical values without the need for a variable declaration. They can take various forms, including integers, decimal numbers, and scientific notation. An integer literal like 100 is straightforward, while a decimal literal like 3.14 includes a fractional component. Scientific notation is used for very large or small numbers, such as 1.2 times 10 to the fifth power, which equals 120,000. These literals are directly usable in calculations and do not require prior data definitions, making them efficient for quick computations. Understanding numeric literals is crucial for handling numerical data effectively in COBOL programs. String literals in COBOL are sequences of characters enclosed in either single or double quotes. They are used to represent text data and can include spaces, punctuation, and special characters. For instance, COBOL and programming are valid string literals, as are more complex examples like hello, world. The choice of quotation marks is flexible, but consistency is important to avoid syntax errors. String literals are commonly used in messages, labels, or data fields where exact text representation is necessary. By using quotes, the compiler recognizes the text as a literal rather than a variable or keyword, ensuring correct program execution. Constants in COBOL are fixed values that remain unchanged throughout the execution of a program. They are defined using the 77 level in the data division, which is specifically reserved for constants. Unlike variables, constants cannot be modified once initialized. For example, the statement 77 max value, pick 95 value 1000 creates a constant named max value with a numeric value of 1000. This approach ensures that critical values, such as fixed rates or thresholds, are consistently applied across the program, reducing the risk of errors from accidental modifications. To define a constant in COBOL, the syntax involves the 77 level, followed by the constant name, a pick clause specifying the data type, and the value clause assigning the literal value. For example, 77 pi, pick 95v92, value 3.14, creates a constant named pi with a numeric value of 3.14, where the pick clause indicates 5 digits before the decimal point and 2 after. This structure ensures clarity and precision in data representation. Constants enhance program readability by replacing hard-coded values with meaningful names, making maintenance easier. They also promote consistency, as changing a constant's value updates all references to it automatically. The working storage section in COBOL is where variables and temporary data are stored during program execution. It is defined using the one level in the data division, which allows for the creation of variables that can be modified as the program runs. Unlike constants, which are fixed, working storage variables hold dynamic data that may change based on input, calculations, or other program logic. This section is essential for storing intermediate results, user inputs or output values, making it a core component of COBOL programs that require data manipulation. Working storage variables in COBOL are defined with specific data types using the pick clause, which determines how the data is stored and processed. For example, one name pick x20 declares a variable named name that can hold up to 20 characters, while one age pick 93 stores a 3-digit numeric value. These variables are used to hold data that may change during program execution, such as user input or calculation results. By structuring variables with appropriate data types, programmers ensure data integrity and efficient memory usage, which is vital for reliable program operation. Literals and constants are frequently used in computations and displays within COBOL programs. For instance, the statement display total 100 outputs the text total, followed by the value 100. Similarly, the ADD statement 50 to 25, giving result, performs an arithmetic operation using literals. Constants, on the other hand, provide stable values for repeated use, such as a tax rate or a fixed threshold. By integrating literals and constants into program logic, developers ensure accuracy and consistency, making the code more efficient and easier to maintain. Best practices in COBOL programming emphasize the use of constants for values that remain unchanged, such as tax rates or currency conversion factors. This approach avoids magic numbers, hard-coded values that are difficult to track and update. Instead, defining these values as constants improves code readability and reduces errors. Additionally, organizing working storage variables logically, such as grouping related data or using descriptive names, enhances maintainability. These practices contribute to cleaner, more reliable programs that are easier to debug and modify over time. In summary, literals provide direct values for immediate use in COBOL programs, while constants ensure fixed, reusable values that enhance consistency. The working storage section holds variables for dynamic data processing, making it essential for program functionality. By mastering these elements, COBOL programmers can create reliable, maintainable, and efficient applications. Properly utilizing literals, constants, and working storage variables is fundamental to successful COBOL development. Input-output operations are fundamental to the functionality of COBOL programs. These operations allow the program to interact with external data sources, enabling the reading of information from files, terminals, or other devices, and the writing of results back to them. COBOL provides a set of specific verbs such as read, write, open, and close that facilitate these interactions. These verbs are designed to handle data flow efficiently, ensuring that programs can process large volumes of data commonly encountered in business and administrative systems. Understanding I/O is crucial because it forms the basis for data processing in real-world applications where programs must retrieve, manipulate, and store data accurately. The file control section in COBOL is responsible for defining how a program interacts with external files. This is accomplished through the file control paragraph, which uses the select statement to associate a file with a program. For example, the statement select input file assign to input dat links the program to an external file named input dat. Files in COBOL can be of different types, such as sequential, indexed, or relative, each offering distinct methods for accessing and managing data. Sequential files are read or written in the order they are stored. Indexed files allow direct access using keys, and relative files use relative positions for data retrieval. This section ensures that the program knows the exact location and structure of the files it uses. In the data division, the file section plays a critical role in defining the structure of the data records that a program processes. This is done using the file section, where each record is described using level numbers, typically starting with 1. For instance, the line 1 employee record defines the structure of a record that holds employee data. Each data item within the record must align precisely with the format of the file to ensure compatibility. This alignment is essential because any mismatch can lead to data corruption or processing errors. The data division acts as a blueprint, ensuring that the program understands how to interpret the data it reads and how to format the data it writes. The procedure division in COBOL contains the logic for performing input-output operations. The first step is to use the open verb to initialize a file for reading or writing. For example, open input file name prepares a file for reading, while open output file name prepares it for writing. Once the file is open, the read verb retrieves data from the file, and the write verb sends data back the file. Finally, the close verb terminates the connection, ensuring that all data is properly saved and system resources are released. These verbs work in sequence to manage the flow of data, making it possible for programs to handle complex data processing tasks. Reading data from a file involves a series of steps to ensure accuracy and reliability. First, the program opens the file in input mode using the open input statement. Next, it uses the read verb to fetch data into a specified data item. It is important to check for the not AT end condition to handle cases where the file has no more data to read. If the read operation is successful, the program processes the data, which might involve calculations, validation, or storage. This process is repeated until the end of the file is reached, ensuring that all data is processed without interruption. Proper handling of end-of-file conditions prevents errors and ensures the program behaves predictably. Writing data to a file follows a structured approach to ensure that the data is correctly formatted and stored. The process begins by opening the file in output mode with the open output statement. The program then uses the right verb to transfer data from a data item to the file. For example, write record name from data item sends the contents of data item to the file. It is crucial to validate the data before writing to avoid errors such as incorrect formats or missing fields. Once all data is written, the program closes the file using the close verb, which finalizes the operation and releases system resources. This step ensures that the data is properly saved and accessible for future use. Error handling in input-output operations is essential to maintain the reliability of COBOL programs. The status clause is used to detect and respond to errors, such as file not found, invalid data, or disk full conditions. For example, the red statement can include an AT end clause to handle cases where the end of the file is reached. Programmers must also validate input data to ensure it meets the required format and constraints. This validation prevents processing errors and ensures that the program can handle unexpected situations gracefully. By implementing robust error handling, COBOL programs can provide meaningful feedback and maintain data integrity even in the face of failures. Here is a sample program that demonstrates basic input-output operations in COBOL. The program starts with the identification division, which assigns a name to the program. The file control paragraph includes the select statement to link the program to an external file named input.dat. The data division defines the file structure in the file section, where the input record is described as a 20-character field. The procedure division contains the logic for opening the file, reading the record, and closing the file. This example illustrates how COBOL programs interact with files, retrieving data and processing it as needed. It serves as a foundation for more complex programs that handle multiple files and advanced data processing tasks. Adhering to best practices in input-output operations ensures that COBOL programs are efficient and reliable. One key practice is to always close files after use to prevent data loss and resource leaks. Using the AT-end clause helps manage end-of-file conditions, avoiding runtime errors. Validating input data before processing ensures that the program can handle unexpected or incorrect data gracefully. Additionally, maintaining consistency between file structures and data definitions prevents mismatches that could lead to errors. These practices not only improve program reliability, but also make maintenance and debugging easier, ensuring that COBOL programs remain functional over time. In conclusion, mastering input-output operations is essential for anyone working with COBOL. These operations form the backbone of data processing in COBOL programs, enabling them to interact with external data sources effectively. Verbs like read, write, open, and close are critical tools for managing data flow, ensuring that programs can retrieve, manipulate, and store data accurately. By practicing with sample programs and following best practices, learners can build a strong foundation in COBOL I/O, as many legacy systems still rely on COBOL. Understanding these concepts is vital for maintaining and evolving these critical applications. Loops are fundamental in programming because they allow us to execute a set of instructions multiple times without repeating code. This not only makes our programs more efficient, but also reduces redundancy, which is crucial for maintaining and updating code. In COBOL, there are several looping constructs that serve different purposes. The primary ones include the perform statement, which is the foundation of all loops in COBOL. variations like perform varying, which is ideal for loops that involve a changing variable, such as a counter. Perform until is used when we want to repeat a block of code until a specific condition becomes true. Lastly, perform times is employed when we need to execute a block of code a fixed number of times. Understanding these constructs helps in writing clean and effective COBOL programs. The perform statement is the cornerstone of looping in COBOL. It allows us to execute a paragraph or a section of code multiple times, which is essential for tasks that require repetition. A paragraph in COBOL is a named block of code that can be called from different parts of the program. When we use the perform statement, we specify the name of the paragraph or section we want to execute. This not only makes the code more organized, but also enhances readability. For instance, if we have a block of code that needs to be run multiple times, we can define it once as a paragraph and then call it using perform. This approach minimizes code duplication and makes the program easier to manage. The perform varying loop is particularly useful when we need to loop while a variable changes. This is commonly used with counters or other variables that increment or decrement during each iteration. For example, if we want to execute a block of code 10 times, we can initialize a counter at 1 and increment it by 1 until it exceeds 10. The syntax for this loop includes the varying clause, which specifies the variable, its starting value, the increment, and the condition to stop. This structure ensures that the loop runs a controlled number of times, making it ideal for scenarios where the number of iterations is determined by a variable. It is also helpful when processing data elements in a sequence, such as iterating through an array or a list. The perform until loop is designed to execute a block of code repeatedly until a specified condition becomes true. This is a post-test loop, meaning the condition is checked after each iteration. For example, if we have a flag variable that starts as n, and we want to keep running the loop until it is set to y, the loop will execute at least once before checking the condition. This makes perform until suitable for situations where the loop must run at least once, such as waiting for user input or processing data until a certain state is reached. It is important to ensure that the condition eventually becomes true to avoid infinite loops, which can cause the program to hang or crash. The perform times loop is used when we need to execute execute a block of code a specific number of times. Unlike other loops that rely on conditions or changing variables, this loop is straightforward and does not require a counter. For instance, if we want to run a block of code 5 times, we can use the perform times statement with the number 5. This is particularly useful in scenarios where the number of iterations is known in advance, such as generating a fixed number of reports or performing a task a set number of times. Since the loop does not depend on external conditions, it is less prone to errors related to variable changes, making it a reliable choice for predictable tasks. Nested loops are loops that are placed inside other loops, allowing us to handle more complex tasks, such as processing multidimensional data. For example, a loop that iterates through rows and another loop that iterates through columns can be used to process a two-dimensional array. However, nested loops require careful management to avoid infinite loops, which can occur if the exit conditions are not properly defined. To ensure clarity and maintainability, it is best practice to use descriptive variable names that indicate their purpose, such as WS row counter or WS column index. This not only makes the code easier to read, but also helps in debugging and future modifications. Let me demonstrate a simple counter loop using the perform varying statement. In this example, we initialize a variable called WS counter to 1 and increment it by 1 each time until it exceeds 5. During each iteration, the program displays the current value of the counter. The loop will execute 5 times, printing the numbers 1 through 5. This example illustrates how the varying clause controls the loop's behavior by modifying the counter variable, ensuring that the loop runs exactly 5 times. Such loops are commonly used in scenarios where we need to process a fixed number of items or perform a task repeatedly with a changing value. In conclusion, looping structures are indispensable in COBOL for handling repetitive tasks efficiently. The perform statement is the primary tool for creating loops, with variations like perform varying, perform, until, and perform times tailored to specific scenarios. Understanding how to use these constructs effectively allows us to write programs that are both efficient and easy to maintain. By following best practices such as avoiding infinite loops and using descriptive variable names, we can ensure that our COBOL programs are reliable and readable. Mastering loops is a critical step in becoming proficient in COBOL programming. Data manipulation is a cornerstone of programming in COBOL, enabling the processing and transformation of data to meet specific business requirements. Whether you are handling customer information, financial records, or inventory details, the ability to manipulate data efficiently is crucial. In this session, we will explore two fundamental verbs in COBOL: the move verb, which is used to copy data from one field to another, and the compute verb, which performs arithmetic operations. These tools form the backbone of data handling in COBOL, and understanding their proper use will empower you to build robust and accurate programs. The move verb is one of the most frequently used commands in COBOL, designed to transfer data from a source field to a destination field. Its syntax is straightforward: move source to destination. This verb is not limited to simple copying. It also handles data type conversions. For example, it can convert numeric values into alphanumeric strings, or vice versa. However, it is important to note that if the source and destination fields have different lengths, the move verb may truncate the data or pad it with spaces to match the destination's size. This behavior can have significant implications for data integrity, so careful attention to field definitions is essential. The syntax of the move verb is structured as move literal or variable to variable. This means you can move a literal value, such as a string or number, directly into a variable, or you can transfer the contents of one variable to another. For instance, moving the literal hello into a greeting variable, or copying the value of a quantity variable into a total variable. The move verb supports a wide range of data types, including alphanumeric, numeric, and mixed formats. This flexibility makes it a versatile tool for data handling, but it also requires careful planning to avoid unintended side effects. Let's look at some practical examples of how the move verb is used. Copying literals is straightforward, such as moving the number 100 into a quantity variable to initialize it. Copying variables involves transferring the value from one variable to another, which is useful for data duplication or reassignment. Additionally, the rounded option can be used to ensure that numeric values are rounded to the nearest decimal place when moved into a destination field with fewer decimal places. For example, moving the value 3.1415 into a variable defined to hold 2 decimal places would result in 3.14, while using rounded would produce 3.14 or 3.15, depending on the context. The compute verb is the primary tool for performing arithmetic operations in COBOL. It allows you to add, subtract, multiply, and divide values, making it ideal for calculations involving numbers, totals, and percentages. The syntax for the compute verb is simple. Compute variable equals expression. This structure enables you to perform complex calculations in a single statement, which is particularly useful for scenarios requiring multiple operations. The compute verb also automatically handles data type conversions, ensuring that numeric values are correctly processed, even when mixed with other data types. The syntax of the compute verb is structured as compute variable equals expression. This means you can assign the result of an arithmetic expression to a variable. For example, multiplying a quantity by a price to compute a total, or calculating a discount based on a percentage. The compute verb supports nested operations and parentheses to control the order of calculations, which is critical for ensuring accuracy. By using parentheses, you can prioritize certain operations over others, preventing errors that might arise from default precedence rules. This flexibility makes the compute verb a powerful tool for handling intricate calculations. Let's explore some practical examples of the compute verb in action. A basic arithmetic operation might involve adding 2 numbers, such as computing a sum by adding 10 and 20. For more complex scenarios, you can perform calculations involving multiple variables and operators, such as WSA plus WSB multiplied by WSC, and then divided by 2. These operations are common in financial calculations, where precision is paramount. Additionally, the compute verb can be used to update variable values dynamically, such as increasing a previous value by a fixed amount. This capability is essential for tasks like updating balances or adjusting totals in real time. While the move and compute verbs are powerful, there are several common pitfalls to avoid. Data type mismatches can lead to unexpected results, such as attempting to move a numeric value into an alphanumeric field. Truncation or rounding errors may occur when the source and destination fields have different lengths, potentially altering the accuracy of your data. Incorrect precedence in compute expressions can also produce erroneous results, highlighting the importance of using parentheses to define the order of operations. Finally, overwriting original data without creating a backup can lead to irreversible data loss. So always ensure that critical information is preserved before performing manipulations. To ensure effective use of the move and compute verbs, follow these best practices. Use the move verb for simple data copying tasks, as it is efficient and straightforward. Reserve the compute verb for complex arithmetic operations that require multiple steps or precise calculations. Always validate data before performing any manipulations to prevent errors and ensure accuracy. Additionally, use comments to explain complex expressions, making your code easier to understand and maintain. These practices will help you write cleaner, more reliable COBOL programs that are both functional and easy to troubleshoot. In conclusion, the move and compute verbs are indispensable tools for data manipulation in COBOL. The move verb excels at copying data, while the compute verb handles arithmetic operations with ease. By mastering these verbs, you will be equipped to tackle a wide range of programming challenges. Remember to practice using these tools with real-world examples to reinforce your understanding and build confidence in your COBOL skills. With consistent practice, you will become proficient in creating efficient and accurate data processing solutions. Arrays and tables in COBOL are essential tools for organizing and managing multiple data items of the same type within a program. These structures allow programmers to group related data under a single name, making it easier to handle large quantities of information efficiently. A table, specifically, is a collection of data items that share a common name and structure, which simplifies operations like searching, sorting, and updating. The OCCUS clause is a fundamental part of defining a table, as it specifies the number of elements the table can hold. By using tables, developers can avoid redundant code and streamline processes that involve repetitive data, such as processing lists of employee names or student grades. This approach not only improves code readability, but also enhances program performance by reducing the need for multiple individual variables. To define a table in COBOL, you use the data division and the OCCURS clause, which determines how many times a data item repeats. For example, the line 1 employee table followed by 5 employee name occurs 10 times pick X20, creates a table that stores 10 entries for employee names, each up to 20 characters long. The OCCURS clause is crucial because it sets the size of the table, ensuring that the program allocates the correct amount of memory. This definition also specifies the data type, such as pick X20 for alphanumeric values. Tables can be single-dimensional, like the example, or multi-dimensional, allowing for more complex data organization. Understanding how to structure tables is the first step in leveraging their power to manage large data sets effectively. Accessing elements within a table in COBOL is done using subscripts or indexes, which act as pointers to specific positions in the table. Subscripts are numeric values that indicate the exact location of an element, such as the 5th entry in a list. For instance, the statement move John to employee name 5 places the name John in the 5th position of the table. Indexes, on the other hand, are more dynamic and are often used with the index keyword to traverse the table programmatically. This is particularly useful when iterating through all elements, as indexes can be adjusted incrementally. By mastering both subscripts and indexes, programmers can efficiently manipulate table data, whether they are updating a single entry or processing the entire table. Table operations in COBOL include initializing values, updating specific elements, and iterating through all entries using loops. Initialization ensures that all elements start with a known state, preventing unexpected results. Updating involves modifying individual elements, such as changing a student's grade or an employee's salary. Iteration is achieved through loops, with the perform varying loop being a common choice for processing each element in sequence. This loop allows the program to perform actions like calculating totals, checking for errors, or applying transformations to every entry. These operations are the backbone of table management, enabling programs to handle tasks that require repetitive processing with minimal code. Sorting and searching tables in COBOL are critical for organizing and retrieving data efficiently. The sort verb arranges table entries in a specific order, such as ascending or descending, based on a key field. example, the statement sort employee table, ascending key employee name, organizes the list of employee names alphabetically. Searching, on the other hand, uses the search verb to locate specific values within the table, which is essential for tasks like finding a particular record. These operations significantly improve data retrieval speed, especially when dealing with large data sets. By incorporating sorting and searching into programs, developers can ensure that data is both accessible and manageable, even as the volume of information grows. Practical examples demonstrate how tables are used in real-world scenarios. For instance, storing student grades in a table allows for easy calculation of averages or identification of high and low scores. Counting occurrences of a specific value, like the number of students with a particular grade, showcases the table's ability to summarize data. Updating employee records using table indexing enables efficient modifications to payroll information. These applications extend to areas like inventory management, where tables track stock levels, and payroll processing, where they manage employee salaries. By applying tables to such tasks, COBOL programs become more scalable and adaptable to complex business needs. Adhering to best practices when working with tables in COBOL ensures reliability and maintainability. Always initializing tables prevents errors caused by uninitialized data, which can lead to unpredictable behavior. Using descriptive names for tables and elements makes the code easier to understand and debug. Validating subscripts is essential to avoid out-of-bounds errors, which occur when accessing positions that do not exist in the table. Finally, documenting table structures provides clarity for future modifications, helping other developers understand the program's logic. These practices not only improve code quality, but also reduce the risk of bugs and simplify long-term maintenance. In conclusion, arrays and tables in COBOL are indispensable for managing large data sets and streamlining repetitive tasks. The OCCURS clause plays a central role in defining these structures, enabling efficient grouping and manipulation of data. Mastery of table operations enhances a programmer's ability to create robust, high-performance applications. By practicing with real-world examples, such as processing student grades or employee records, learners can solidify their understanding and apply these concepts effectively in professional settings. Tables are a cornerstone of COBOL programming, and their proper use is key to building scalable and efficient solutions. Strings in COBOL are sequences of characters that are defined using the pick X clause. This clause specifies that a field is a character string, and each position in the string holds a single character. String handling in COBOL involves a variety of operations, such as manipulating, combining, and extracting data from these character sequences. This is essential for processing text-based information in applications, such as names, addresses, and log entries. For example, when dealing with user input or data from external files, COBOL programs frequently need to handle strings to perform tasks like formatting, validation, or data transformation. Understanding how to work with strings is fundamental for building robust applications that interact with textual data. COBOL provides built-in functions that simplify string manipulation. The string function concatenates multiple strings into a single string, making it useful for combining parts of data. The inspect function allows for character-level operations, such as counting occurrences of a specific character or replacing characters within a string. The unstring function splits a string into multiple fields based on specified delimiters, which is critical for parsing structured data. Additionally, the function length returns the length of a string, enabling programs to validate input or manage dynamic data sizes. These functions are foundational tools for any COBOL programmer working with text, as they streamline complex operations that would otherwise require manual loops or conditional logic. The string statement in COBOL is used to combine multiple strings into one. Its syntax includes specifying source strings, which can be delimited by a space or a specific character, and an optional destination field where the result is stored. For instance, if a program needs to create a full name from separate first and last name fields, the string statement can efficiently concatenate them. The delimited by clause allows precise control over how the strings are joined, ensuring that the output meets the required format. This functionality is particularly valuable when constructing messages, generating reports, or preparing data for further processing. Mastery of the string statement enhances a programmer's ability to handle dynamic text in COBOL applications. The inspect statement in COBOL is designed for character-level operations, offering two primary capabilities: tallying and replacing. Tallying allows a program to count how many times a specific character appears in a string, which is useful for tasks like analyzing text for frequency of vowels or special characters. Replacing, on the other hand, enables the modification of characters within a string, such as substituting spaces with underscores or converting uppercase letters to lowercase. These operations are vital for data cleaning and formatting, ensuring that strings meet specific requirements before further processing. By leveraging inspect, COBOL programs can perform efficient and targeted changes to textual data. The unstring statement in COBOL is used to split a single string into multiple fields based on specified delimiters. This is particularly useful for parsing structured data, such as comma-separated values or fixed-width records. The syntax includes identifying the source string, the delimiters, and the destination fields where the split data will be stored. A pointer variable can also be used to track the current position within the string during the split process. For example, a CSV string like John Doe 123 main sent can be divided into individual fields for first name, last name, and address. This functionality is essential for processing external data sources and integrating them into COBOL applications. In practice, the string statement is used to combine values into a single string. For example, if two variables hold hello and world, the string statement can join them into hello world or hello world, depending on the delimiter. The inspect statement is equally powerful, as demonstrated by replacing all instances of a specific character, such as converting A to X in a string. These examples illustrate how COBOL's string functions simplify complex operations, reducing the need for lengthy code. By mastering these tools, programmers can efficiently handle tasks like data formatting, error checking, and information extraction, making their applications more versatile and reliable. When working with strings in COBOL, it is crucial to follow best practices to ensure reliability and correctness. Always initializing strings helps avoid unexpected characters that might result from uninitialized variables, which is a common issue in COBOL due to its fixed-length data structures. Using the delimited by clause provides precise control over how strings are combined or split, preventing errors caused by ambiguous delimiters. Validating input length is another key step, as it prevents truncation or overflow that could corrupt data. Testing edge cases, such as empty strings or excessive delimiters, ensures that the program handles all possible scenarios gracefully. These practices are essential for developing robust and error-free COBOL applications. String handling is a critical skill for anyone working with COBOL, as it underpins the ability to process and manipulate text-based data effectively. The string, inspect, and unstring statements are powerful tools that enable programmers to perform complex operations with minimal code. By applying best practices, such as initializing variables, validating input, and testing edge cases, developers can create applications that are both efficient and reliable. These techniques are particularly important in legacy systems, where text processing remains a core function. Mastering string handling in COBOL not only enhances data manipulation capabilities, but also ensures that programs can adapt to a wide range of real-world scenarios. File handling in COBOL is a fundamental concept that allows programmers to store, retrieve, and manipulate data efficiently. This is particularly important in applications that deal with large volumes of data, such as banking systems, inventory management, and transaction processing. COBOL provides two primary types of file handling mechanisms: random files and indexed files. Random files enable direct access to specific records using a key field, which acts as a unique identifier for each record. This makes them ideal for situations where you need to quickly locate a single record based on a known key. Indexed files, on the other hand, use an index structure to locate records, which allows for more flexible data retrieval. The index serves as a roadmap, guiding the program to the correct location in the file. Understanding these two types is essential for designing efficient COBOL programs that can handle data with speed and precision. Random files are particularly useful when the goal is to access specific records directly using a key. For example, if you have a customer database and need to retrieve a customer's information by their unique ID, a random file would allow you to do this without scanning the entire file. The key field in a random file must be unique, meaning no two records can share the same key. This uniqueness is critical because it ensures that each record can be identified and accessed without ambiguity. In COBOL, the access mode for random files is specified using the access mode is random clause in the file description entry. This tells the compiler that the file will be accessed directly based on the key. Common operations on random files include reading, writing, updating, and deleting records, all of which require the use of the key field. For instance, the read statement with a key clause allows the program to fetch a specific record, while the update statement modifies it. These operations are efficient and straightforward, making random files a good choice for applications where exact key lookups are frequent. Indexed files take a different approach by using an index to locate records, which provides greater flexibility compared to random files. The index is built on one or more fields, which can be primary or secondary. The primary index is typically based on a unique key, while secondary indexes allow for additional access paths. For example, a customer file might have a primary index on the customer ID and a secondary index on the customer's last name, enabling searches by name as well. In COBOL, the access mode for indexed files is specified using the access mode is INDEXED clause. This allows the program to perform both direct and sequential access. Direct access is similar to random files, where the index is used to locate a specific record quickly. Sequential access, on the other hand, allows the program to read records in the order they are stored in the file, which is useful for tasks like generating reports. The use of indexes makes indexed files highly versatile, as they can handle a wide range of queries, from exact matches to range searches. The key differences between random and indexed files lie in their structure, performance, and use cases. Random files require a unique key field for direct access, ensuring that each record can be retrieved instantly. This makes them faster for scenarios where exact matches are needed, such as looking up a record by a unique identifier. Indexed files, however, do not require a unique key, but instead rely on an index to locate records. This index can be built on multiple fields, allowing for more complex queries. For instance, an indexed file can efficiently handle range searches, such as finding all records where a certain field falls between two values. While random files offer speed for exact lookups, indexed files provide flexibility for a broader range of queries. However, this flexibility comes at a cost. as indexed files require additional storage to maintain the index structures. Programmers must weigh these trade-offs based on the specific requirements of their applications. Implementing random and indexed files in COBOL involves several steps, starting with defining the file in the file control section of the data division. This section specifies the external file name and the access mode. For random files, the access mode is declared as access mode is random, while indexed files use access mode is indexed. The file description entry, or FD, defines the structure of the file and includes the key field for random files. In random files, the key field is specified using the key is clause, which tells the compiler that this field will be used for direct access. For indexed files, the indexed clause is used to indicate that an index is present, and multiple keys can be defined if needed. For example, a customer file might have a primary index on the customer ID and a secondary index on the customer's name. These definitions ensure that the program can efficiently access the data based on the specified keys and indexes. Proper implementation of these clauses is crucial for the correct functioning of the file handling mechanisms in COBOL. Random files offer several advantages that make them suitable for specific applications. Their primary benefit is the ability to access records directly using a key, which results in faster retrieval times compared to sequential access. This is particularly useful in scenarios where the program frequently needs to look up records by a known key, such as in a payroll system where employee IDs are used to retrieve salary information. Random files are also simpler to implement for small datasets, as the overhead of maintaining an index is not required. This simplicity makes them a good choice for applications with limited data volume and straightforward access requirements. However, it is important to note that random files rely on the uniqueness of the key field, which must be carefully managed to avoid data integrity issues. Despite these limitations, their speed and ease of use make random files a valuable tool in COBOL programming. Indexed files provide significant advantages for applications that require complex data retrieval. Unlike random files, which are limited to exact key lookups, indexed files can handle a wide range of queries, including range searches and multi-field searches. For example, a sales database might use an indexed file to find all transactions within a specific date range, or to search for records based on multiple criteria, such as region and product type. The flexibility of indexed files comes from their ability to support multiple access paths, allowing the program to retrieve data in different ways. This makes them ideal for large, dynamic datasets where the access patterns are not predictable. Additionally, indexed files can accommodate changes to the data more efficiently, as the index can be updated without reorganizing the entire file. These features make indexed files a powerful choice for applications that require robust and adaptable data management. While both random and indexed files have their strengths, they also come with certain disadvantages that programmers must consider. One major limitation of random files is the requirement for a unique key field for every record. If the key field is not properly maintained, it can lead to data duplication or inconsistencies, which can be challenging to resolve. Additionally, random files are less efficient for queries that involve ranges or partial matches, as they are designed for exact key lookups. Indexed files, on the other hand, may introduce performance overhead due to the need to maintain the index structure. Every time a record is added, modified, or deleted, the index must be updated, which can slow down these operations. This makes indexed files less suitable for applications with high update frequencies. Both file types require careful design and planning to ensure optimal performance, and programmers must choose the appropriate method based on the specific needs of their applications. To ensure effective file handling in COBOL, it is essential to follow best practices that maximize efficiency and reliability. When working with random files, choosing the right key field is critical. The key should be unique, stable, and frequently used to avoid unnecessary overhead. For indexed files, maintaining the index regularly is important to prevent performance degradation, especially in large datasets. This can involve tasks like reorganizing the file or rebuilding the index to keep it optimized. Programmers should also carefully select the access mode based on the application's requirements, as using the wrong mode can lead to inefficiencies. For example, using a random access mode for a file that requires range queries would be inappropriate. Testing file operations thoroughly is another crucial step, as it helps identify potential issues such as incorrect key usage or index prevents corruption. By adhering to these best practices, programmers can ensure that their COBOL applications handle data effectively and reliably. In conclusion, random and indexed files are essential tools for efficient data management in COBOL programming. Random files excel in scenarios where direct access to specific records is required, offering speed and simplicity for exact key lookups. Indexed files, by contrast, provide greater flexibility for complex queries and multiple access paths, making them suitable for large and dynamic datasets. Understanding the differences between these two file types is crucial for making informed decisions about their use in different applications. By selecting the appropriate file type and implementing it correctly, programmers can design COBOL applications that are both efficient and scalable. Whether the goal is to retrieve a single record quickly or to handle complex data queries, the right choice of file handling mechanism can significantly impact the performance and reliability of the program. Subprograms are essential components in COBOL programming that allow developers to create reusable code blocks within a larger program. These blocks help break down complex tasks into smaller, manageable parts, which enhances modularity, making the overall program easier to understand and maintain. By reusing these code segments, developers save time and reduce errors that might arise from duplicating code. Subprograms can be categorized into two main types: subroutines, which perform a task without returning a value, and functions, which produce a result that can be used elsewhere in the program. Additionally, subprograms can be either internal, meaning they are defined within the same program, or external, where they exist as separate programs that can be called from other programs. This flexibility allows for greater organization and scalability in large-scale applications. The structure of a subprogram in COBOL begins with the Program ID clause, which uniquely identifies the subprogram and serves as its entry point. Following this, the subprogram contains a procedure division where the actual logic and instructions are written. This division is similar to the main program's procedure division, but is specific to the subprogram's purpose. Every subprogram must have a clear entry point, such as a named procedure or the main section, to ensure the program knows where to start executing the subprogram's code. The subprogram concludes with an end program statement, or the specific end program ID clause, signaling the end of its definition. This structured approach ensures that subprograms are well defined and easy to integrate into larger programs. The call statement is the primary mechanism for invoking a subprogram in COBOL. Its basic syntax is straightforward, with the subprogram name enclosed in quotes, such as call subprogram name. However, the power of the call statement lies in its ability to pass parameters to the subprogram. Parameters can be passed using the using clause for input data and the giving clause for output data. For example, the statement call calculate using WS input giving WS result demonstrates how data is transferred between the main program and the subprogram. This capability allows subprograms to interact dynamically with the rest of the application, making them versatile tools for handling specific tasks. When passing parameters to a subprogram, the using clause is used to send data into the subprogram, while the giving clause is used to receive data back. It is crucial that the parameters match in type, order, and length to avoid runtime errors or incorrect results. For instance, if a subprogram expects a numeric value, passing a string could lead to unexpected behavior. Additionally, COBOL allows variables to be passed by reference or by value, depending on the version and compiler settings. Passing by reference means the subprogram works with the original data, while passing by value creates a copy, protecting the original data from modification. Understanding these distinctions is key to ensuring data integrity and program reliability. Common errors when using the call statement often stem from simple oversights. One frequent issue is an incorrect subprogram name or a missing linkage, which can prevent the program from locating the subprogram entirely. Mismatched parameter types or counts can also cause critical failures, as the subprogram may not interpret the data correctly. For internal subprograms, the contains clause is essential to inform the compiler that the subprogram is part of the same program, ensuring proper linking. Additionally, improper use of the using and giving clauses can lead to data corruption, where the subprogram modifies data unintentionally or fails to return expected results. These errors highlight the importance of careful coding and thorough testing to maximize the effectiveness of subprograms. Developers should adhere to best practices that promote clarity and reliability. First, each subprogram should focus on a single, well-defined task to maintain simplicity and ease of maintenance. Using meaningful names for subprograms and their parameters makes the code more readable and reduces confusion. Documenting the purpose of each subprogram, along with the expected input and output, ensures that other developers can understand and use them correctly. Finally, testing subprograms independently before integrating them into the main program helps identify and resolve issues early, preventing cascading errors in the larger application. These practices contribute to a more robust and efficient code base. In summary, subprograms are a cornerstone of structured COBOL programming, enabling efficient code organization and reuse. The call statement allows for modular execution, making it easier to manage complex applications by breaking them into smaller components. Proper handling of parameters is critical, as even minor mistakes can lead to significant issues. By following best practices, such as keeping subprograms focused, using clear naming conventions, and thoroughly testing each component, developers can avoid common pitfalls and build reliable, maintainable programs. Subprograms not only enhance productivity, but also contribute to the long-term success of COBOL applications. Debugging is the process of identifying and resolving errors in COBOL programs. These errors can take various forms, such as syntax errors, which are violations of the language rules, logical errors, which occur when the program runs but produces incorrect results, and runtime exceptions, which happen during execution due to unexpected conditions. Effective debugging ensures that programs function as intended, delivering reliable and correct outcomes. It is a critical skill for any COBOL developer, as even minor issues can lead to significant problems in real-world applications. Common debugging tools include the display statement, which allows developers to output variable values during runtime, providing insights into the program's state. Compiler warnings and error messages are invaluable for catching syntax issues early, as they highlight potential problems before the program is executed. Additionally, debuggers such as the IBM debug tool enable step-by-step execution, allowing developers to pause, inspect, and trace the program's flow. These tools work in tandem to help identify and resolve issues efficiently. Syntax error detection involves checking for missing periods, which which are essential in COBOL to terminate statements. Incorrect verb usage, such as using the wrong command for a specific operation, can also cause errors. Invalid data types, like assigning a character value to a numeric field, must be addressed. Validating file structures and record definitions ensures that data is read and written correctly. The copy statement is a powerful feature that helps reuse code, reducing redundancy and minimizing the risk of errors. Logical error identification requires tracing the program's flow using display statements or debuggers to pinpoint where the logic deviates from expectations. Comparing expected results with actual outcomes for key variables can reveal discrepancies. Testing edge cases, such as maximum or minimum input values, helps uncover hidden flaws that might not appear during normal operation. This systematic approach ensures that the program behaves correctly under all conditions. Data validation techniques are essential for ensuring input consistency. The inspect statement can check for specific characters or patterns in strings, while the string statement helps combine data accurately. Validating numeric fields for invalid values, such as negative amounts in a context where only positive numbers are allowed, prevents erroneous calculations. Ensuring that null or uninitialized variables are handled properly avoids unpredictable behavior during program execution. Error handling in COBOL involves using the ON size error clause to catch numeric overflow during calculations, which can prevent the program from terminating abruptly. Implementing status clauses for file operations allows developers to detect issues such as file not found or access violations. Custom error routines or tools like CBLTSD can provide more detailed diagnostics, enabling the program to respond gracefully to exceptions rather than crashing. The display statement is a fundamental tool for tracking variable states during runtime. By inserting display statements at critical points, developers can monitor how data changes as the program executes. Conditional display statements, such as checking if a variable exceeds a threshold, allow targeted debugging. However, it is crucial to remove or comment out these statements in production code to avoid unnecessary output and maintain performance. Step-by-step execution using a debugger allows developers to control the program's flow, executing one line at a time. This method helps observe how memory is used and how variables change over time. Pausing at breakpoints enables a closer inspection of the program's state, making it easier to identify where issues arise. This technique is particularly useful for complex programs where the error source is not immediately apparent. Debugging with the ON size error clause is essential for handling numeric overflow in calculations. For example, when dividing one number by another, if the result exceeds the variable's capacity, the ON size error clause can trigger a specific action, such as displaying an error message. This prevents the program from terminating unexpectedly and allows for controlled error recovery, ensuring continued operation even in the face of invalid inputs. File handling issues often stem from errors in opening or closing files, which can be detected using the status clause. Validating file existence and access permissions ensures that the program can read from or write to the correct location. Resolving record read-write issues requires careful use of the read and write statements, ensuring that data is processed accurately and that file pointers are managed correctly. Data type mismatches can lead to unexpected behavior if not addressed. Ensuring compatibility between variables, such as matching numeric and alphanumeric fields, is critical. The function numval can convert string values to numeric types, but developers must be cautious about invalid conversions. Avoiding implicit data type conversions, which can cause subtle errors, is a best practice for maintaining program integrity. Common debugging pitfalls include overlooking trailing spaces in string comparisons, which can lead to incorrect matches. Misusing perform loops, such as creating infinite loops due to incorrect conditions, can cause the program to hang. Forgetting to initialize variables may result in unpredictable values being used in calculations. Addressing these pitfalls requires attention to detail and thorough testing. Best practices for debugging include maintaining clean modular code that is easy to navigate and troubleshoot. Documenting assumptions and edge cases helps other developers understand the program's behavior. Using version control systems allows teams to track changes and revert to stable versions if issues arise. These practices foster a more reliable and maintainable code base. Debugging requires patience, systematic analysis, and proficiency with tools. Prioritizing code readability and robust error handling programs are easier to maintain and less prone to failures. Practicing with real-world scenarios helps developers build the skills needed to diagnose and resolve complex issues efficiently. Continuous learning and attention to detail are key to mastering this essential aspect of COBOL programming. Error handling is a critical aspect of programming that ensures applications can respond appropriately to unexpected conditions during execution. In COBOL, this is achieved through the use of the status clause, which allows developers to monitor and track errors that occur during file operations. File status codes, which are numeric values, provide specific information about the nature of an error, enabling precise troubleshooting. By implementing robust error handling mechanisms, programs become more reliable as they can gracefully manage issues rather than crashing or producing incorrect results. This not only improves the user experience, but also simplifies the debugging process, allowing developers to quickly identify and resolve problems. Proper error handling is essential for maintaining data integrity and ensuring that applications operate smoothly even in the face of unexpected challenges. File status codes in COBOL are two-digit numeric values stored in a data item, typically a two-character field. These codes provide a standardized way to represent errors that occur during file operations. The first digit of the code indicates the general type of error, such as success, duplicate entries, or file access issues. For example, a first digit of 0 usually signifies success, while a 2 might indicate a duplicate key. The second digit of the code offers additional details about the specific error, helping developers pinpoint the exact issue. Common codes include 0 for success, 2 for a duplicate key during an insert operation, 4 for a file not found or inaccessible, and 5 for a record not found during a read. Understanding these codes is essential for effective debugging and ensuring that programs respond appropriately to various error conditions. Let's explore some of the most commonly encountered file status codes in COBOL. A status code of 0 indicates that the operation was successful with no errors. Code 2 typically arises when a duplicate key is encountered during an insert, which is common in databases with unique key constraints. Code 4 signifies that the file could not be found or is inaccessible, often due to incorrect file names or path issues. Code 5 is used when a record is not found during a read operation, which might happen if the data does not exist in the file. Code 10 indicates that the end of the file has been reached, which is a normal condition, but still requires handling. Code 14 points to an invalid record length, which could occur if the record structure does not match the file definition. Code 23 is triggered during a search for an invalid key, and Code 99 serves as a general catch-all for unspecified errors. Familiarity with these codes allows developers to create more resilient and user-friendly applications. To implement error handling in COBOL, developers must first declare a data item to store the file status. This is typically a 2-character field, such as file status pic x2. Next, the status clause is included in the file description FD entry, which associates the file with the data item. For example, the FD entry might look like FD file name status is file status. This setup ensures that after every input-output operation, the status of the file is recorded in the data item. By checking the status after each operation, developers can detect and respond to errors in real time. This practice is crucial for maintaining the integrity of data and ensuring that programs handle issues without crashing or leaving the system in an inconsistent state. Once the file status is stored, developers can use if statements to handle errors based on the status code. A common approach is to check if the status is not equal to 00, which indicates a successful operation. For example, if the status is 2, the program might display a message indicating a duplicate key error. Similarly, a status of 04 could trigger a message about a file not being found. This allows the program to provide specific feedback to users or initiate recovery procedures. In addition to displaying messages, developers can implement logic to retry operations, log errors, or terminate the program gracefully. The key is to ensure that each error is addressed appropriately, preventing the program from proceeding with incorrect or incomplete data. Let's look at an example of how error handling is implemented in a COBOL program. The file definition might include a status clause, as in FD file name status is file status. During a read operation, the program might use the read statement with an AT-end clause to set the status to 10 when the end of the file is reached. After the read, the program checks the file status field if it is not 0, the program invokes an error routine to handle the issue. This structure ensures that every file operation is followed by a status check, allowing the program to respond to errors immediately. By integrating these checks into the code, developers can create applications that are more reliable and easier to maintain. To ensure effective error handling in COBOL programs, there are several best practices to follow. First, always check the file status after every input-output operation, as this is the primary way to detect errors. Logging errors with descriptive messages helps in debugging, as it provides a record of what went wrong. Using display or write statements can inform users of critical issues, making the program more transparent. For unrecoverable errors, it is important to implement graceful termination, which involves closing files and releasing resources before exiting. Finally, testing programs with edge cases, such as missing files or invalid data, ensures that error handling mechanisms work as intended. These practices contribute to the overall reliability and robustness of COBOL applications. In summary, error handling is a fundamental aspect of writing reliable COBOL programs. File status codes provide valuable insights into the nature of errors, allowing developers to address issues effectively. The status clause and if statements are essential tools for monitoring and responding to errors during file operations. By following best practices such as thorough status checks, detailed logging, and graceful termination, developers can create programs that are resilient to unexpected conditions. These strategies not only improve the user experience, but also make maintenance and debugging more efficient. As a result, proper error handling is a cornerstone of successful COBOL programming. The data division in COBOL is the foundation for organizing and manipulating data within a program. Today, we will explore advanced topics that go beyond basic variable declarations. Mastering these concepts allows developers to create more efficient and scalable applications. By understanding complex data structures, you can optimize memory usage and improve program performance. Our objectives today include enhancing your ability to handle intricate data operations and ensuring your code is both robust and maintainable. Let's begin by examining how COBOL manages manages multi-dimensional data through the OCCURS clause. The OCCURS clause is a powerful tool for defining arrays in COBOL. It allows you to specify how many times a data item should repeat, effectively creating a table. Nested tables take this a step further by enabling hierarchical data representation. For example, you might use a table to store employee records, where each record contains another table for their dependents. Practical examples include processing customer orders with multiple line items, or managing inventory with categories and subcategories. Manipulating these tables requires careful use of subscripts and indexes to access specific elements. Understanding nested tables is essential for handling real-world data that often has layered structures. Redefines and Level 66 offer unique ways to manage data storage and naming. The Redefines clause allows you to reinterpret the same memory location as different data types. This is useful for scenarios where a single storage area needs to represent varying data formats. Level 66, on the other hand, provides a mechanism to rename variables without duplicating data. For instance, you might rename a field for clarity in a specific section of code while maintaining its original name elsewhere. These features help eliminate redundancy and ensure data consistency. By leveraging Redefines and Level 66, you can write more concise and maintainable code. Level 77 and Level 88 are specialized for constants and condition checks. Level 77 is used to declare single-value variables, often serving as constants that remain unchanged throughout a program. Level 88, however, introduces condition names, which allow you to define meaningful names for specific values. For example, you might create a condition name, high value, to check if a variable exceeds a threshold. This improves code readability by replacing cryptic numerical checks with descriptive names. These features make your code easier to understand and maintain, especially in large programs with complex logic. Pointers and references in COBOL enable dynamic data handling. The address of clause retrieves the memory address of a variable, which can then be assigned to a pointer. The set statement allows you to manipulate these pointers, enabling operations like traversing linked lists or dynamically allocating memory. This is particularly useful for applications requiring flexible data structures. However, working with pointers requires caution to avoid issues like memory leaks or invalid references. Understanding how to use these features effectively can greatly enhance your ability to manage complex data scenarios. Data manipulation techniques in COBOL involve commands like move, inspect, and string. The move statement transfers data between variables, while inspect is used for character-level operations such as counting or replacing specific characters. String concatenates multiple fields into a single string. Subscripts and indexes are critical for navigating tables, allowing you to access elements in a structured way. Error handling is equally important, as it ensures your program can gracefully handle unexpected data or invalid inputs. These techniques form the backbone of many COBOL applications, especially those dealing with large datasets. Best practices for the data division focus on clarity, efficiency, and maintainability. Organizing your data sections logically makes it easier to locate and modify variables. Avoiding redundancy through redefines and renaming reduces the risk of inconsistencies. Documentation is also key, as it helps others understand your code. For example, adding comments to explain complex data structures or the purpose of specific redefines can save time during future maintenance. By following these practices, you create code that is not only functional, but also easy to work with over time. In summary, advanced data division concepts empower you to build more sophisticated and efficient COBOL programs. From nested tables to pointers and condition names, each feature plays a role in structured data handling. Remember, the goal is to write code that is both powerful and easy to maintain. As you continue your training, apply these techniques to real-world scenarios to deepen your understanding. Practice will help you master these tools and become a more effective COBOL developer. Thank you for your attention. Welcome to this session on handling dates and times in COBOL. COBOL provides built-in functions that make it easier to work with date and time data, which is essential for applications ranging from financial systems to data logging. Understanding date and time formats is critical because incorrect formatting can lead to errors in data processing, reporting, and even system failures. For example, a date stored as 2/12/2023 could mean February 12th or December 2nd, depending on the region. This session will cover the date, time, and timestamp functions, as well as techniques for manipulating and formatting these values effectively. By the end, you will have a solid foundation for working with time-sensitive data in COBOL programs. Let's explore the key functions COBOL offers for date and time operations. The function current date returns the current date and time in a standardized format, which is useful for logging events or tracking transaction times. The function date gives the current date in the format YYYYMMDD, making it ideal for date comparisons or calculations. The function time returns the current time in HHMMSS format, which is handy for timing operations or generating unique identifiers. Finally, the function timestamp combines both date and time into a single value, often used in database records or audit trails. These functions are fundamental for any program that needs to interact with real-time data. COBOL uses specific data types to store date, time, and timestamp values. The date data type holds values in the format YYYYMMDD, allowing for straightforward date arithmetic. The time data type stores values in HHMMSS, which is useful for time-based calculations like determining durations. The timestamp data type combines both, storing values as YYYYMMDDHHMMSS, making it suitable for precise time tracking. These data types are not just for storage. They are used in calculations, comparisons, and formatting. For instance, you can subtract two timestamps to find the difference between two events, or compare dates to validate user input. Understanding these types is key to building robust applications. Manipulating dates and times in COBOL involves using arithmetic operations and specialized functions. The ADD and subtract verbs allow you to adjust dates and times by specific units. For example, adding 10 days to a date variable can be done with ADD10 to date value. The function date of integer converts an integer into a date, which is useful for working with date serial numbers. Conversely, the function integer of date converts a date into an integer, enabling calculations like determining the number of days between two dates. These tools are essential for tasks such as scheduling, aging reports, or validating date ranges. Formatting date and time output ensures that values are presented in a way that is readable and consistent. The edit clause allows you to define custom formats for displaying dates and times. For example, you can format a date as MMDDYYYY to match regional standards. When using the function current date, you might move the result to a working storage variable, and then apply the edit clause to restructure it. For more complex formatting, statements like inspect or string can be used to concatenate time components or insert separators like slashes or colons. Proper formatting is crucial for user interfaces, reports, and data exchange with other systems. Common date and time operations include calculating differences between dates, validating inputs, and handling time zones. For example, subtracting two dates can reveal how many days have passed between two events, which is useful in payroll or project management systems. Validating dates ensures that values like 2020-30-230 are rejected, preventing errors. Time zone conversions require custom logic or external libraries, since COBOL does not natively support this. Similarly, daylight saving time adjustments demand additional programming to account for time shifts. These operations highlight the importance of thorough testing and clear documentation when working with time-sensitive data. Let's look at some practical code examples. The statement move function current date to WS current date retrieves the current date and time, which can then be formatted for display. Adding days to a date is straightforward with ADD5 to WS date, which increments the date by 5 days. Comparisons like if WS date, WS other date then allow you to check if one date is later than another. For time formatting, the string statement concatenates hour, minute, and second variables into a single time value. These examples demonstrate how COBOL's functions and syntax simplify date and time management in real-world applications. To ensure reliability, follow these best practices. Always validate date and time inputs to catch errors like invalid formats or out-of-range values. Use consistent formatting across your program to avoid confusion, especially when data is shared between systems. Document time zone and daylight saving considerations, as these can affect calculations. Prefer the function current date over older methods like using system variables, as it is more portable and less error-prone. These practices will help you build programs that are both accurate and maintainable when when troubleshooting date and time issues. Start by checking for invalid formats, such as February 30th or 24-hour times exceeding 59 minutes. Ensure that date and time variables are initialized properly, as uninitialized data can lead to unpredictable results. Use display statements to print intermediate values and verify their correctness. Pay special attention to edge cases like leap years, month-end dates, or time zone transitions, which can cause unexpected behavior. Debugging these issues requires patience and a systematic approach to isolate the root cause. In conclusion, mastering date and time handling in COBOL enhances data accuracy and program reliability. The built-in functions simplify complex operations, but their effective use requires understanding their nuances. Practice manipulating and formatting dates and times to reinforce your skills, and always consider edge cases like invalid dates or time zone changes. By applying these techniques, you will be well equipped to develop robust applications that handle time-sensitive data with confidence. Thank you for your attention. Screen programming in COBOL is a fundamental aspect of creating interactive applications that allow users to engage with the program through input and output operations. This approach is particularly useful in environments where direct user interaction is required, such as in banking systems, inventory management, or customer service interfaces. The key components of screen programming include the display statement, which is used to present information to the user, the accept statement, which captures user input, and the screen section, which defines the layout of the user interface. By leveraging these elements, developers can build applications that are not only functional, but also user-friendly, enabling seamless communication between the program and the end user. This focus on interactivity makes screen programming an essential skill for anyone working with COBOL in real-world scenarios. At the core of screen programming in COBOL are the display and accept statements, which serve as the primary tools for user interaction. The display statement allows the program to output messages, prompts, or data to the screen, making it easier for users to understand what action is required. For example, a simple program might use display, enter your name, to prompt the user for input. The accept statement then captures the user's response, storing it in a variable for further processing. This combination of displaying information and gathering input forms the foundation of any interactive COBOL application. By mastering these statements, developers can create programs that respond dynamically to user actions, ensuring a more intuitive and efficient experience. Screen formatting techniques in COBOL provide greater control over how information is presented to the user, enhancing readability and usability. The line and column clauses allow developers to position text precisely on the screen, ensuring that data is displayed in a structured and organized manner. For instance, using line 10, column 5 can place a message at a specific location, making it easier for users to locate important information. Additionally, the blank line statement helps separate sections of the screen, creating visual breaks that improve the overall user experience. When combined with display and accept, these formatting tools enable the creation of well-structured interfaces that guide users through complex interactions. This level of control is particularly valuable in applications where clarity and organization are critical. Validating user input is a crucial step in ensuring the accuracy and reliability of COBOL applications. By using if conditions, developers can check the data entered by the user against specific criteria, such as ensuring that a field is not left blank or that a number falls within a defined range. For example, an if statement might verify whether a name variable contains spaces, indicating that the user has not provided a valid input. If invalid data is detected, the program can respond by displaying an error message, such as invalid input, to inform the user of the issue. This proactive approach to validation helps prevent errors from propagating through the system, making the application more robust and user-friendly. Incorporating validation into screen programming ensures that only correct data is processed, improving the overall quality of the software. Advanced screen interaction in COBOL involves the use of the screen section to create complex and dynamic user interfaces. This feature allows developers to define multiple fields, such as input boxes, labels, and buttons, in a structured layout. By mapping these fields to variables in the data division, the program can efficiently transfer data between the user interface and the internal logic of the application. The move statement plays a key role in this process, enabling the transfer of values from user input fields to working storage variables. Additionally, screens can be updated dynamically using display and accept, allowing the program to respond to user actions in real time. This level of interactivity is essential for applications that require a high degree of user engagement, such as forms, data entry systems, or menu-driven interfaces. Effective error handling and feedback mechanisms are vital for creating user-friendly COBOL applications. When errors occur, such as invalid input or unexpected conditions, the program should provide clear and concise messages to guide the user toward a solution. The display statement is often used to show error messages, while if statements detect and respond to specific issues. Example: if a user enters incorrect data, the program can display a message like "Please enter a valid value" and prompt the user to try again. This approach not only helps users understand what went wrong, but also prevents the program from crashing or behaving unpredictably. Finally, after resolving errors, the program should terminate gracefully using the stop-run statement, ensuring that all resources are properly released and the user is aware that the process is complete. In conclusion, screen programming in COBOL is a powerful tool for creating interactive applications that enhance the user experience. By mastering the display, accept, and screen section components, developers can build interfaces that are both functional and intuitive. The ability to format screens, validate input, and handle errors ensures that applications are reliable and easy to use. As COBOL continues to play a role in legacy systems and critical business processes, the skills learned in screen programming remain highly relevant. Whether developing simple data entry forms or complex transactional systems, the principles discussed in this presentation provide a solid foundation for creating robust and user-friendly COBOL applications. COBOL is a programming language designed specifically for business applications that require robust data storage and retrieval. It has been a cornerstone in industries like finance, healthcare, and government for decades, enabling organizations to manage critical operations. Databases, on the other hand, serve as centralized repositories for storing large volumes of structured data, allowing for efficient access, modification, and management. The integration of COBOL with databases is essential because it allows programs to interact with these data stores, perform complex processing and ensure that data is both accurate and accessible. This synergy is vital for maintaining the integrity and efficiency of business systems, especially when dealing with high transaction volumes and long-term data retention. To understand how COBOL interacts with databases, we must first explore key concepts like database management systems, or DBMS. These systems, such as IMS, DB2, and SQL databases, provide the infrastructure for organizing, storing, and retrieving data. In COBOL, data manipulation is a core function, allowing developers to insert, update, delete, and retrieve records from databases. This process is facilitated through specific COBOL commands and structures. Additionally, the file control section in COBOL plays a critical role in linking programs to database files. It acts as a bridge, ensuring that the program knows where to find the data and how to access it. This section is fundamental for establishing a reliable connection between the COBOL code and the underlying database systems. When working with databases in COBOL, several clauses are used to define the relationship between the program and the data. The database clause specifies the name of the database and any necessary connection details, such as the location or access parameters. The using clause is used to pass variables or parameters to the database, allowing for dynamic interactions. Finally, the access mode clause determines how data is retrieved, whether sequentially, randomly, or through other methods. These clauses are essential for tailoring the program's behavior to the specific requirements of the database, ensuring that data is accessed efficiently and accurately. Together, they form the backbone of database integration in COBOL applications. The file control section in COBOL is a critical component for mapping program files to database tables or datasets. This section acts as a configuration layer, instructing the compiler on how to link the program's data structures to the physical files in the database. For example, the statement "select employee file assign to EMPDB" tells the program that the employee file is associated with the database named EMPDB. This mapping ensures that when the program reads or writes data, it interacts with the correct database file. Without proper file control settings, the program would not know where to find the data, leading to errors or inefficiencies. This section is a foundational element in the integration process, enabling enabling seamless communication between COBOL programs and databases. COBOL supports multiple data access methods, each suited to different scenarios. Sequential access reads records in the order they are stored, making it ideal for processing large datasets in a linear fashion. Indexed access, on the other hand, uses keys to retrieve records directly, which is much faster for specific queries. For instance, a primary index might allow you to find a record by its unique identifier, while a secondary index could retrieve records based on other attributes. Relative access is another method that retrieves records based on their physical position within the file, which is useful for applications requiring direct, position-based data retrieval. Choosing the right access method depends on the nature of the data and the operations required, ensuring optimal performance and efficiency. One of the most powerful features of COBOL is its ability to integrate with SQL, the standard language for relational databases. This is achieved through embedded SQL, where SQL statements are incorporated directly into COBOL code. For example, the code exec SQL select name into EMP name from employee, where ID equals EMPID and exec, allows the program to query a database for an employee's name based on their ID. This integration enables COBOL programs to leverage the full capabilities of relational databases, such as complex queries, joins, and transactions. It also allows developers to take advantage of modern database features while maintaining the reliability and structure of COBOL, making it a versatile tool for both legacy and contemporary systems. Transaction processing is a critical aspect of database operations, ensuring that data remains consistent and reliable. COBOL supports this through commands like commit and rollback, which manage the state of transactions. When a transaction is committed, all changes are permanently saved to the database, while a rollback undoes any changes if an error occurs. This functionality is essential for maintaining ACID properties atomicity, consistency, isolation, and durability, which guarantee that transactions are processed reliably. For example, in a banking application, a transaction involving multiple steps must either complete entirely or be rolled back to prevent partial updates that could compromise data integrity. These features make COBOL a trusted choice for applications where data accuracy is paramount. The integration of COBOL with databases offers numerous advantages, particularly in large-scale business systems. COBOL's ability to handle vast amounts of data efficiently makes it ideal for applications like payroll processing, inventory management, and financial transactions. Its programs are often reusable across different database environments, reducing development time and costs. Additionally, COBOL's scalability allows it to adapt to growing data demands, ensuring that systems can evolve without requiring complete overhauls. These benefits make COBOL a valuable asset for organizations that rely on robust, long-term data management solutions. By combining COBOL's strengths with modern database technologies, businesses can achieve both stability and flexibility in their operations. While COBOL and database integration offer significant benefits, they also present challenges that require careful attention. Performance tuning is crucial, as inefficient queries or poor indexing can lead to slow response times. Developers must analyze and optimize database structures to ensure fast access to data. Error handling is another key area, as database failures can disrupt operations. Implementing robust exception handling mechanisms helps the program recover gracefully from such issues. Security is equally important, with measures like encryption and access controls protecting sensitive data from unauthorized access. By addressing these challenges proactively, developers can build reliable and secure systems that meet the demands of modern business environments. In conclusion, COBOL remains a vital language for integrating with databases, particularly in legacy systems that continue to support critical business functions. Its ability to interact with databases through specific clauses, file controls, and SQL integration ensures that it can adapt to evolving technological landscapes. Understanding these concepts is essential for developing applications that are efficient, secure, and scalable. By following best practices and addressing challenges proactively, developers can harness the full potential of COBOL and databases, ensuring that their systems remain reliable and effective for years to come. This integration not only preserves the value of existing infrastructure, but also provides a foundation for future innovations. SQL integration allows COBOL applications to communicate with relational databases, which are structured collections of data organized into tables. This capability enables developers to retrieve specific information from databases, store new data, and modify existing records using SQL commands. By leveraging SQL, COBOL programs can perform complex data operations that would otherwise require extensive custom coding. This integration not only simplifies database interactions, but also ensures that applications can scale effectively as data volumes grow. For example, a COBOL program might use SQL to fetch customer details from a database, process them, and update account balances without needing to manage the underlying database structure directly. To incorporate SQL into COBOL programs, developers use the exec SQL statement, which acts as a bridge between COBOL and SQL. This syntax allows SQL commands to be embedded directly within COBOL code, making it possible to execute database operations like querying or updating data. However, COBOL alone cannot interpret SQL, so a precompiler is required to translate these embedded SQL statements into standard COBOL code. This precompiler handles the conversion, ensuring compatibility with the COBOL compiler. Additionally, SQL can be executed in two ways: static SQL, where the queries are fixed at compile time, and dynamic SQL, which allows queries to be constructed and executed at runtime based on user input or other variables. This flexibility is particularly useful in applications that require adaptive data handling. Common SQL statements used in COBOL include select, which retrieves data from database tables by specifying conditions and columns. Insert, update, and delete are used to add, modify, or remove records in a database, respectively. These commands form the foundation of data manipulation in relational databases. For schema management, statements like create, alter, and drop are essential. Create is used to define new database structures. Alter modifies existing ones, and drop removes them entirely. Together, these SQL commands allow developers to manage both the data and the structure of the database, ensuring that COBOL applications can adapt to changing business requirements. For instance, a payroll system might use create to establish a new table for employee records, and alter to add a column for tax information. Host variables serve as the interface between COBOL programs and SQL statements, allowing data to be passed back and forth. These variables are declared in the COBOL code and referenced within SQL commands sequence, enabling the program to interact with database fields. When a SQL query returns multiple rows of data, cursors become essential. A cursor acts as a pointer to the result set, allowing the program to process each row individually. By using the fetch statement, developers can retrieve rows one at a time, which is particularly useful for handling large datasets. For example, a COBOL application might use a cursor to iterate through a list of customer orders, processing each order sequentially and updating inventory levels as needed. Transaction control is critical for maintaining data consistency and integrity during database operations. The commit statement ensures that all changes made during a transaction are permanently saved to the database, while rollback undoes any changes if an error occurs. By grouping related operations into a transaction, developers can prevent partial updates that might leave the database in an inconsistent state. The begin and end statements define the scope of a transaction, marking the start and end of a sequence of SQL operations. For instance, in a banking application, a transaction might involve transferring funds from one account to another, and using commit or rollback ensures that either both accounts are updated correctly or neither is affected if an error arises. Error handling in SQL integration relies on the SQL Communication Area, or SQLCA, which stores information about the success or failure of SQL operations. The SQLCOD field within SQLCA provides numeric codes that indicate the outcome of a database action, such as a successful execution or a specific error. By checking the value of SQLCOD, developers can implement conditional logic to handle errors gracefully. The whenever statement further automates this process by triggering predefined actions, such as logging an error or terminating a program when certain conditions are met. This proactive approach to error handling reduces the risk of runtime failures and improves the reliability of COBOL applications. Performance considerations are vital when integrating SQL with COBOL to ensure efficient database interactions. Minimizing the number of database round trips by batching multiple operations into a single request can significantly reduce latency. Optimizing SQL queries by using appropriate indexes, avoiding unnecessary data retrieval, and structuring joins effectively also enhances performance. Additionally, proper schema design, such as normalizing tables to reduce redundancy, ensures that queries run smoothly. For example, a COBOL application processing thousands of transactions might benefit from batch processing to reduce the load on the database server, while well-designed indexes allow for faster data retrieval. These practices collectively contribute to more responsive and scalable applications. SQL integration transforms COBOL applications by enabling them to interact with relational databases, expanding their capabilities beyond traditional file-based processing. Mastering embedded SQL allows developers to build more efficient and flexible applications that can handle complex data operations with ease. By practicing with real-world scenarios, such as developing a customer management system or a financial reporting tool, learners can reinforce their understanding and apply these concepts effectively. As businesses continue to rely on robust data management systems, the ability to integrate SQL with COBOL remains a valuable skill for maintaining and modernizing legacy applications. Modular programming is a fundamental approach in software development that involves breaking down complex programs into smaller, manageable, and independent sections. This method allows developers to focus on specific parts of a program, making the overall structure more organized and easier to handle. In the context of COBOL, modular programming is particularly valuable because it enhances the readability, maintainability, and scalability of code. By dividing programs into distinct modules, sections, and procedures, developers can ensure that each part of the code has a clear purpose and function. This not only simplifies the process of writing and understanding code, but also makes it easier to update or debug specific components without affecting the entire program. The key concepts of modular programming include modules, which are self-contained units of code, sections, which are logical groupings within a module, and procedures, which are sequences of instructions designed to perform a specific task. These elements work together to create a structured and efficient programming environment. In COBOL, sections are essential tools for organizing code logically and improving the overall structure of a program. A section is essentially a named group of statements that are grouped together to perform a specific function or represent a logical unit of code. using sections, developers can create a more coherent flow of instructions, making the program easier to navigate and understand. Sections are defined using the section clause, which marks the beginning of a section, and they are terminated with the end section phrase. This syntax allows for clear delineation between different parts of the program, enabling better management of complex code bases. For example, a section might handle input processing, another might manage calculations, and a third could be responsible for output. This organization not only improves readability, but also supports collaborative development, as multiple team members can work on different sections without conflicting with each other. The structure of a section in COBOL follows a specific syntax that ensures clarity and consistency. The basic format begins with the section name, followed by a period, and then the statements that make up the section. The section is concluded with the end section phrase. This structure allows for a hierarchical organization of code, where sections can contain other sections, paragraphs, or executable statements. For instance, a main section might include several smaller sections, each handling a distinct aspect of the program. The example provided, main logic section, illustrates how a section can be named to reflect its purpose, such as managing the core operations of a program. By embedding paragraphs or additional sections within a larger section, developers can create a layered structure that enhances modularity. This approach is particularly useful in large-scale COBOL applications, where maintaining a clear and logical flow of code is critical for long-term maintenance and scalability. Using sections in COBOL offers numerous benefits that contribute to the overall quality and efficiency of a program. One of the primary advantages is improved code organization, as sections allow developers to group related statements and procedures in a logical manner. This organization makes it easier to locate and modify specific parts of the code without disrupting the entire program. Additionally, sections facilitate debugging and testing by isolating specific functions, enabling developers to focus on one section at a time. This targeted approach reduces the complexity of identifying and resolving issues. Another significant benefit is the potential for code reuse across multiple programs. Sections can be designed as reusable components that are incorporated into different applications, saving time and effort in development. Finally, sections simplify maintenance and updates, as changes can be made to a single section without affecting the rest of the program. This modularity ensures that COBOL programs remain adaptable and easier to manage over time. In COBOL, sections and paragraphs serve different but complementary roles in structuring code. While sections are designed to group multiple paragraphs or other sections into a larger logical unit, paragraphs are typically used for smaller, individual tasks. A section might contain several paragraphs that handle different aspects of a process, such as input validation, data processing, and output generation. For example, a section dedicated to input processing could include paragraphs for reading data, checking for errors, and storing the information. This distinction allows developers to create a structured hierarchy where sections manage broader functions and paragraphs handle specific actions. Sections are ideal for organizing complex operations, while paragraphs are suited for concise, focused tasks. Understanding this difference is crucial for designing COBOL programs that are both efficient and easy to maintain. Let's take a closer look at an example of a section in COBOL. The code snippet provided demonstrates a section named main logic section, which includes a series of statements. The first statement, display welcome to COBOL, outputs a message to the user, setting the stage for the program's execution. The subsequent lines, perform initialize process and perform calculate result, instruct the program to execute specific procedures. This structured approach ensures that the code is executed in a logical sequence, making it easier to follow and maintain. The use of the perform statement allows the program to call other sections or paragraphs, promoting modularity and reusability. By grouping related instructions within a section, developers can create a clear and organized flow of execution, which is essential for both understanding and debugging the program. This example highlights how sections contribute to a well-structured COBOL application. To maximize the effectiveness of sections in COBOL, it is essential to follow best practices that promote clarity, efficiency, and maintainability. One key practice is to use descriptive names for sections, such as input processing or calculation logic, which immediately convey their purpose to other developers. Keeping sections focused on a single task ensures that they remain manageable and less prone to errors. Avoiding deeply nested sections is also important, as excessive nesting can complicate the code structure and make it harder to navigate. Additionally, documenting sections with comments or explanations helps others understand their role within the program. These practices collectively enhance the readability and maintainability of COBOL code, making it easier for teams to collaborate and for future developers to work with the code base. By adhering to these guidelines, developers can create high-quality modular programs that are both efficient and easy to manage. In summary, modular programming and the use of sections are vital components of effective COBOL development. By dividing programs into logical units, developers can create code that is more organized, reusable, and easier to maintain. Sections provide a structured framework for grouping related statements, enabling efficient execution and debugging. Following best practices ensures that these sections are well designed and contribute to the overall quality of the program. As COBOL continues to be used in critical applications, mastering the use of sections and modular programming techniques is essential for producing clean, scalable, and maintainable code. By applying these principles, developers can enhance the efficiency and readability of their COBOL programs, ensuring they meet the demands of modern software development. File maintenance refers to the process of updating, modifying, or managing data stored in files. This is a critical aspect of programming because it ensures that data remains accurate, consistent, and efficient within applications. When data is stored in files, it is often subject to changes over time, such as adding new information, correcting errors, or removing outdated records. These operations are essential for maintaining the reliability of any system that relies on stored data. For example, in a payroll system, employee records may need to be updated when salaries change or when new staff are hired. The way files are organized also plays a significant role in how efficiently these operations can be performed. Common file organizations include sequential access, where records are stored and retrieved in the order they were added, indexed access, which uses an index to quickly locate specific records, and random access, which allows direct retrieval of records using a unique identifier. Choosing the right file organization is crucial for optimizing performance and ensuring that data can be accessed and modified as needed. There are several types of file operations that programmers must understand when working with COBOL. Sequential access is one of the most straightforward methods, where records are processed in the order they are stored in the file. This approach is often used for batch processing, such as reading through a list of transactions from start to finish. In contrast, random access allows for direct retrieval of records by using a specific key or record number, making it ideal for applications that require quick access to specific data points, like a customer database. Indexed access is another method that uses an index to locate records efficiently, combining the benefits of both sequential and random access. For instance, an index might be created for a file containing employee records, allowing the system to quickly find a particular employee based on their ID. Each of these methods has different implications for performance and data management. Sequential access is often slower for large files, but simpler to implement, while indexed or random access can significantly improve retrieval speed, but may require more complex setup. Understanding the strengths and limitations of each method helps programmers design systems that are both efficient and scalable. When it comes to updating data in COBOL, there are several techniques that can be used to ensure accuracy and efficiency. The rewrite statement is specifically designed to modify existing records in a file, making it a powerful tool for updating information without having to delete and reinsert the record. For example, if an employee's salary needs to be adjusted, the rewrite command can directly update the relevant field in the file. In addition to modifying records, programmers can use the add and delete statements to insert or remove records from a file. These operations are fundamental for maintaining up-to-date data, such as adding new customer information or removing obsolete entries. However, these actions must be handled carefully to preserve data integrity. Record locking is a crucial concept here, as it prevents multiple users or processes from modifying the same record simultaneously, which could lead to conflicts or data corruption. Transaction handling is another important aspect, as it ensures that updates are either fully completed or rolled back in case of errors, maintaining the consistency of the data. Finally, data validation is essential before performing any updates. This involves checking that the input data meets the required criteria, such as correct formatting or valid values, to prevent errors that could compromise the system's reliability. Effective file maintenance requires a set of strategies to ensure data is protected, organized, and accessible. One of the most critical strategies is backup and recovery, which involves regularly copying files to a secondary location to prevent data loss in case of hardware failure, corruption, or other disasters. For example, a company might schedule daily backups of its financial records to ensure that data can be restored quickly if needed. Transaction logging is another essential practice, where every change to the file is recorded in a log. This allows for auditing and enables the system to roll back changes if an error occurs, ensuring data consistency. File reorganization is also important, particularly for large files that may become fragmented over time. By reordering or restructuring the data, programmers can improve access speed and reduce storage overhead. In addition to these strategies, the open and close statements play a vital role in managing file access. The open statement prepares the file for reading or writing, while the close statement ensures that all changes are saved and the file is properly released for other processes. These steps are crucial for maintaining the stability and efficiency of file operations. To ensure reliable data updates in COBOL, it is essential to follow best practices that prioritize accuracy, consistency, and system stability. One of the first steps is data validation, which involves checking input data against predefined rules to ensure it is correct and appropriate. For example, if a program is designed to accept only numeric values for a salary field, it must verify that the input meets this requirement before proceeding. Record locking is another key practice, as it prevents multiple users or processes from modifying the same record at the same time. This is particularly important in multi-user environments where concurrent access could lead to conflicts or data inconsistencies. Error handling is also critical, as it allows the program to detect and respond to issues such as file access failures, invalid data, or unexpected interruptions. By implementing robust error handling routines, programmers can ensure that the system remains stable and that errors are resolved without causing further damage. Finally, documentation is essential for maintaining consistency clarity in file maintenance procedures. Detailed records of how files are structured, updated, and managed help ensure that all team members follow the same practices, reducing the risk of mistakes and making it easier to troubleshoot issues when they arise. In conclusion, file maintenance and data updates are fundamental to the success of any COBOL application. These processes ensure that data remains accurate, consistent, and accessible, which is vital for the smooth operation of any system. The choice of file access method, whether sequential, random, or indexed, depends on the specific requirements of the application, such as the volume of data, the frequency of access, and the need for speed. Prioritizing data integrity and implementing proper error handling during updates is essential to prevent errors and maintain the reliability of the system. Regular practice and adherence to best practices, such as data validation, record locking, and transaction logging, further enhance the efficiency and stability of file management. By following these principles, programmers can build robust COBOL applications that are capable of handling complex data operations while minimizing the risk of errors or data loss. Ultimately, a strong understanding of file maintenance and data updates is a cornerstone of effective COBOL programming. In this session, we will begin by revisiting the fundamental concepts of string and numeric operations in COBOL. These basics include tasks like moving data between fields, performing simple arithmetic, and handling character strings. However, as data processing becomes more complex, it is essential to master advanced techniques. These techniques allow us to handle intricate data transformations, ensuring accuracy and efficiency in programs that process large volumes of information. Today's topics will focus on 3 key areas: advanced string manipulation, numeric validation, and precision handling. By the end of this training, you will have the tools to tackle sophisticated data challenges with confidence. Let us explore the power of advanced string operations in COBOL. The string verb enables the concatenation of multiple fields into a single string, which is invaluable when combining parts of a name or address. Conversely, the unstring verb allows us to split a single string into multiple fields, such as separating a date into day, month, and year. The inspect verb is a versatile tool for tasks like replacing specific characters or counting occurrences of a particular character within a string. Reference modification, which involves using subscripts or indexes, lets us extract or update specific portions of a string without altering the entire field. Finally, we will discuss the function trim, which removes leading and trailing spaces, ensuring that data is clean and ready for further processing. These techniques are critical for handling real-world data that often contains inconsistencies. Moving on to numeric operations, we will examine how COBOL performs arithmetic tasks. Verbs like compute, add, subtract, and multiply allow us to perform calculations, but it is equally important to validate numeric data. The numeric condition checks whether a field contains only numeric characters, preventing errors during calculations. When dealing with decimal values, the decimal point is divided directive ensures that the decimal point is treated as a divisor, which is crucial for accurate financial or scientific computations. Additionally, we must implement error checking to handle invalid numeric input, such as non-numeric characters in a field intended for numbers. These steps are vital for maintaining data integrity and avoiding runtime errors. In this section, we will combine string and numeric techniques to solve more complex problems. For instance, the function numval can extract numeric values from strings that contain non-numeric characters, such as parsing a price from a formatted string like $19.99. The edit and CER features allow us to format numeric fields for output, ensuring that numbers are displayed consistently. Using inspect, we can clean up numeric data by removing unwanted characters before conversion. A practical example involves processing input strings that contain commas or currency symbols, which must be cleaned and converted into numeric values to calculate totals. This integration of string and numeric operations is essential for applications that handle mixed data formats. As we conclude this session, let us discuss best practices and common pitfalls to avoid. Overflow in numeric operations can lead to incorrect results or program crashes, so using value checks ensures that calculations stay within acceptable limits. Proper alignment in string operations is critical to prevent data corruption, especially when working with fixed-length fields. The redefines clause provides flexibility by allowing different interpretations of the same data storage, which is useful for scenarios requiring multiple data views. Finally, debugging complex string and numeric logic requires careful testing and the use of display statements to trace data flow. By following these practices, you can build robust and reliable COBOL programs. To recap, we have explored advanced string manipulation, numeric validation, and precision handling in COBOL. These techniques are foundational for managing complex data processing tasks with accuracy and efficiency. Remember that precision, validation, and flexibility are key to developing reliable applications. I encourage you to practice these concepts through real-world scenarios, such as processing financial data or parsing text files. If you have any questions or need further clarification on any topic, please feel free to ask during the Q&A session. Thank you for your attention, and I hope this training enhances your proficiency in COBOL. COBOL, which stands for Common Business-Oriented Language, was created in the late 1950s to address the growing need for a standardized programming language in the business sector. At the time, companies struggled with fragmented systems, and COBOL provided a unified approach for tasks like payroll, inventory, and financial transactions. Over the decades, it became the backbone of critical infrastructure in industries such as banking, government, and healthcare. Legacy systems, which are older software or hardware still in use today, often rely on COBOL because they have been refined over years to meet specific business needs. These systems, though outdated, continue to support essential operations, making their maintenance and modernization a pressing concern for organizations worldwide. Modernizing legacy systems is not just a technical challenge, but a strategic imperative. As these systems age, the cost of maintaining them escalates due to the scarcity of skilled COBOL developers, many of whom are nearing retirement. This shortage creates a bottleneck for updates and troubleshooting. Additionally, legacy systems often lack compatibility with contemporary technologies like cloud computing, artificial intelligence, and application programming interfaces, which are now foundational for innovation. Security vulnerabilities also multiply over time, as older systems may not support modern encryption or compliance standards. For organizations, failing to address these issues can lead to operational inefficiencies, increased risks, and missed opportunities to leverage cutting-edge solutions. The process of modernizing COBOL systems is fraught with complexities. Monolithic applications, which are large, self-contained programs, are particularly challenging to restructure. These systems often lack clear documentation, making it difficult to understand their architecture and functionality. The risk of data loss or system downtime during migration is significant, as any error in the process could disrupt critical operations. Furthermore, organizations may face internal resistance to change, as employees and stakeholders are accustomed to existing workflows. Overcoming these hurdles requires careful planning, robust testing, and a commitment to balancing innovation with the preservation of reliable, time-tested systems. To navigate the challenges of modernization, organizations can adopt several strategies. Rehosting involves moving COBOL applications to modern platforms, such as cloud environments, without altering the code itself. This approach can reduce infrastructure costs and improve scalability. Refactoring, on the other hand, requires rewriting COBOL code into more modern languages like Java or Python, which may offer better performance and integration capabilities. Hybrid approaches leverage middleware to connect COBOL systems with new technologies, allowing for gradual transitions. Automation tools, such as code analyzers and migration assistants, can streamline the process by identifying inefficiencies and generating code templates, thereby reducing manual effort and minimizing errors. Real-world examples highlight the effectiveness of these strategies. One major bank successfully migrated its COBOL-based core banking systems to Java-based microservices, enabling faster development cycles and improved scalability. Government agencies have utilized COBOL to cloud platforms to modernize their systems, achieving greater flexibility and cost savings. In the retail sector, companies have integrated COBOL systems with AI-driven analytics tools, allowing them to process real-time data for personalized customer experiences. These case studies demonstrate that modernization is not a one-size-fits-all solution, but a tailored process that adapts to the unique needs of each organization. A variety of tools are available to support COBOL modernization. IBM's Rational Developer for COBOL offers advanced features for debugging, testing, and refactoring COBOL code, making it a popular choice for enterprises. Open COBOL, an open-source compiler, provides cross-platform compatibility, allowing developers to work in diverse environments. Automated COBOL to Java or COBOL to Python converters can assist in rewriting code, though they require careful validation to ensure accuracy. Containerization technologies like Docker and Kubernetes enable COBOL applications to run in modern, scalable environments, improving deployment efficiency and resource management. These tools collectively empower organizations to modernize their systems while maintaining reliability and performance. Successful modernization hinges on adherence to best practices. Conducting thorough risk assessments and pilot projects allows organizations to identify potential pitfalls and test solutions in controlled environments. Involving stakeholders from the outset ensures that all perspectives are considered, fostering buy-in and collaboration. Prioritizing critical systems for migration helps allocate resources effectively, focusing on areas that deliver the most value. Maintaining backward compatibility during transitions is equally important, as it minimizes disruptions and ensures a smooth transition for users and processes. By combining these practices, organizations can navigate the complexities of modernization with confidence and precision. In conclusion, COBOL remains a cornerstone of legacy systems, but its continued relevance depends on strategic modernization. While preserving the functionality of these systems is essential, organizations must also embrace innovation to stay competitive. Modernization efforts can unlock new capabilities, enhance security, and align legacy systems with contemporary technologies. However, this process requires a balance between maintaining stability and fostering change. By investing in continuous learning, adapting strategies to evolving needs, and leveraging the right tools, organizations can ensure the long-term viability of their systems while driving progress in a rapidly changing technological landscape. Security in legacy systems is a critical concern because many organizations still rely on COBOL applications to manage essential operations such as financial transactions, government records, and healthcare data. These systems often operate in environments where updates are infrequent, making them vulnerable to modern threats. Unsecured COBOL applications can expose sensitive data to breaches, leading to financial loss, regulatory penalties, and reputational damage. To address these risks, modern security practices must be integrated into legacy COBOL environments. This includes adopting proactive measures such as input validation, encryption, and access control, while respecting the constraints of older systems. By combining traditional COBOL techniques with contemporary security frameworks, developers can ensure these critical applications remain resilient against evolving threats. Validating user inputs is a foundational step in securing COBOL applications. Every piece of data entering the system, whether from a keyboard, file, or network, must be checked for type, length, and format to prevent malicious or malformed entries. For example, a field expecting a numeric value should reject alphabetic characters, and a field with a maximum length of 10 characters should not accept longer inputs. COBOL provides tools like the inspect verb to analyze and modify data, and the string verb to concatenate and sanitize strings. These functions help remove unwanted characters or structure data properly. Additionally, setting strict limits on data fields, such as defining fixed-length variables, can prevent buffer overflows, which occur when data exceeds allocated memory space. By implementing these practices, developers reduce the risk of exploits that target input handling weaknesses. Secure coding practices in COBOL require careful attention to program structure and data handling. The use of GO to statements can lead to uncontrolled program flow, making it difficult to track logic and identify vulnerabilities. Instead, developers should favor structured programming techniques like nested if statements or perform loops to maintain clarity. Hard-coding sensitive values, such as passwords or API keys, within the code is a dangerous practice because it exposes these secrets if the code is compromised. Instead, these values should be stored in external configuration files or encrypted databases. Reusable secure code modules can be created using the copy statement, which allows developers to share common logic across multiple programs. This not only improves consistency, but also simplifies maintenance and reduces the likelihood of errors. Encryption is essential for protecting sensitive data in COBOL applications, especially when dealing with personal information, financial records, or confidential communications. COBOL includes built-in verbs like encrypt to secure data at rest, such as files stored on disk, and in transit, such as data sent over networks. However, encryption alone is not sufficient. Secure key management is equally important. Keys must be stored in protected environments, such as hardware security modules or encrypted vaults, and never hard-coded into the application. Developers should also implement mechanisms to rotate keys periodically and restrict access to authorized personnel only. By combining encryption with robust key management, organizations can ensure that even if data is intercepted or accessed without authorization, it remains unreadable and unusable to attackers. Access control and authentication are vital for preventing unauthorized users from performing critical operations in COBOL applications. Before allowing access to sensitive functions, such as updating a database or processing transactions, the system must verify the user's identity through strong authentication methods like passwords, multi-factor authentication, or biometrics. Role-based access control, RBAC, further enhances security by assigning permissions based on user roles, ensuring that individuals only have access to the resources necessary for their tasks. For example, a junior clerk might have read-only access to certain files, while an administrator can modify them. Securing file and database access also involves configuring operating system permissions, using encrypted connections, and regularly reviewing access logs to detect suspicious activity. Auditing and logging provide a critical layer of security by tracking and recording events that could indicate vulnerabilities or breaches. Security-relevant events, such as failed login attempts, unauthorized access attempts, or changes to sensitive data, should be logged to create an audit trail. In COBOL, this can be achieved using the right statement to append entries to a log file, including timestamps, user identifiers, and descriptions of the actions taken. These logs serve as a historical record that can be analyzed to identify patterns of suspicious behavior. Regularly reviewing logs is essential, as it allows teams to detect anomalies early and respond to threats before they escalate. Automated tools can also be used to monitor logs in real time, alerting administrators to potential issues. COBOL applications are susceptible to several common vulnerabilities that developers must be aware of. One such risk is SQL injection, which occurs when untrusted input is used to manipulate embedded SQL statements, potentially allowing attackers to execute unauthorized commands. For example, a poorly validated input field could be exploited to access or modify database records. Another vulnerability arises from the insecure use of call and link statements, which allow programs to invoke external modules. If these calls are not properly restricted, they could lead to the execution of malicious code. Additionally, inadequate error handling can result in information leakage, where error messages expose system details that attackers can exploit. Addressing these issues requires rigorous testing, input validation, and the implementation of secure coding practices. A variety of tools are available to enhance the security of COBOL applications. Static code analyzers, such as CA Intertest and CompuWare, automatically scan source code for potential vulnerabilities, such as insecure practices or outdated libraries. These tools can identify issues like hard-coded passwords or improper memory usage. Encryption libraries, often provided by third-party vendors, enable developers to integrate robust encryption algorithms into their COBOL programs without reinventing the wheel. Automated vulnerability scanners designed for legacy systems can detect known weaknesses, such as outdated protocols or misconfigurations, and provide recommendations for remediation. By leveraging these tools, organizations can proactively address security gaps and improve the overall resilience of their COBOL applications. Prioritizing security throughout the COBOL development lifecycle is essential for maintaining the integrity of legacy systems. This involves incorporating security considerations during the design, coding, testing, and deployment phases. Regular updates and patches are necessary to address newly discovered vulnerabilities, even in systems that have been in use for decades. Developers should also stay informed about modern security frameworks and adapt them to fit the constraints of COBOL environments. By combining the strengths of legacy COBOL practices with contemporary security strategies, organizations can ensure their critical applications remain secure, compliant, and capable of meeting evolving business needs. This proactive approach not only protects data, but also extends the lifespan of valuable legacy systems. Unit testing in COBOL involves verifying individual programs or sections of code to to ensure they function correctly in isolation. This process is essential because COBOL is often used in legacy systems where even small errors can have significant consequences. By focusing on individual components, developers can identify and fix issues early in the development cycle, which saves time and resources. Unit testing also helps confirm that the logic within a program is sound and that potential errors are detected before the code is integrated into larger systems. This practice is especially critical for maintaining and updating old COBOL systems, which may lack modern testing frameworks. The importance of unit testing in COBOL cannot be overstated. Complex applications built with COBOL often have intricate dependencies and long execution paths, making debugging a time-consuming task. Unit testing reduces this burden by isolating parts of the code, allowing developers to pinpoint issues more efficiently. It also enhances the reliability of the code by ensuring that each component behaves as expected under various conditions. Additionally, unit testing supports regression testing, which is vital when making updates or modifications to existing systems. By running tests after changes, teams can quickly identify if new updates have introduced unintended side effects. Testing in COBOL requires a combination of tools and techniques to simulate real-world scenarios. One approach is to use test harnesses, which are specialized programs designed to provide input and capture output for the code under test. These harnesses allow developers to control variables and test edge cases without relying on external systems. Another valuable tool is the COBOL debugger, such as the IBM debug tool, which enables step-by-step execution and inspection of program flow. For larger projects, automation is key. Developers can write batch jobs or scripts to run tests repeatedly, ensuring consistency and saving time during frequent testing cycles. Writing effective test cases in COBOL starts with identifying the critical functions or procedures that need validation. These might include data processing routines, business logic, or input-output operations. Once the targets are determined, developers create mock data sets that represent various input scenarios, such as valid data, invalid entries, or boundary conditions. Defining expected outputs is equally important, as it provides a clear benchmark for evaluating the program's behavior. By documenting these test cases, teams can ensure that future changes do not inadvertently break existing functionality. Executing and debugging tests in COBOL involves running the code within the appropriate runtime environment, often using a COBOL compiler. This step helps verify that the program compiles and runs without syntax errors. During execution, developers use breakpoints and logs to monitor the program's behavior, tracking how data flows through the system. If a test fails, analyzing the failure patterns can reveal underlying issues in the code. This iterative process of testing, debugging, and refining ensures that the program meets its requirements and performs reliably under different conditions. Validation in COBOL is a crucial step to ensure data integrity and compliance with business rules. Developers must check that data adheres to specific constraints, such as numeric ranges, date formats, or required fields. For example, a program processing financial transactions might validate that amounts are positive and within acceptable limits. COBOL provides constructs like if statements and condition codes to enforce these checks. By integrating validation logic directly into the code, developers can prevent invalid data from propagating through the system, reducing the risk of errors in downstream processes. Testing and validation in COBOL often face unique challenges, particularly with legacy systems. One common issue is working with code that has minimal documentation, making it difficult to understand the original intent. Inconsistent data formats in input files can also complicate testing, as the program may need to handle unexpected or malformed data. Additionally, developers sometimes overlook edge cases, such as extreme values or rare scenarios, which can lead to hidden bugs. Addressing these challenges requires careful planning, thorough documentation, and a proactive approach to testing. Adopting best practices for testing and validation in COBOL can significantly improve the quality of the code. Modularizing the code into smaller, self-contained units allows for more focused testing, making it easier to isolate and fix issues. Documenting test scenarios and their expected outcomes ensures that future developers can understand and maintain the tests. Regularly updating test cases to reflect system changes is also essential. as it keeps the tests relevant and effective. By following these practices, teams can build a robust testing framework that supports long-term maintenance and reliability. In conclusion, unit testing and validation are indispensable for creating reliable COBOL applications. While automated testing provides efficiency and consistency, manual testing ensures that complex scenarios are thoroughly examined. Prioritizing validation helps prevent runtime errors and data corruption, which are critical in systems that handle sensitive or critical information. By combining these approaches, developers can ensure that COBOL programs remain stable, efficient, and adaptable to evolving business needs. Web services are a fundamental technology that allows different systems to communicate and share data over a network. This is achieved through standardized protocols such as SOAP, which stands for Simple Object Access Protocol, and REST, which stands for Representational State Transfer. These protocols define the rules for how systems interact. For example, SOAP relies on XML, a structured format for data, while REST often uses JSON, a lightweight format that is easier to read and write. The ability to exchange data in these formats enables seamless integration between systems, whether they are built on different platforms or technologies. One of the most significant advantages of web services is their role in connecting legacy systems, like those still running COBOL, with modern applications. This bridge allows organizations to leverage their existing infrastructure while adopting new technologies, ensuring that no system is left behind in the digital transformation. COBOL, despite being a programming language that dates back to the 1950s, continues to play a vital role in critical industries such as banking, government, and healthcare. Many of these sectors rely on COBOL-based systems for core operations, such as processing transactions or managing large databases. However, as technology evolves, the challenge lies in modernizing these legacy systems to work with contemporary tools. This is where COBOL's integration with web services becomes essential. By enabling COBOL systems to communicate with web services, organizations can automate processes, share data in real time, and scale their operations. For instance, a COBOL application might send customer data to a cloud-based analytics tool or retrieve information from an external service. Yet, This modernization comes with hurdles. Legacy code can be complex and difficult to maintain. Ensuring compatibility between old and new systems requires careful planning, and addressing security vulnerabilities in aging software is a constant concern. Integrating COBOL with web services involves the language acting as either a client or a server. As a client, COBOL can send requests to web services and process the responses. As a server, it can expose its own functionality through APIs. To achieve this, developers often use tools like IBM's WebSphere, which provides a platform for building and managing web services, or XML parsers that handle structured data. The process begins by defining service contracts, which outline the expected interactions between systems. These contracts ensure that both the COBOL application and the web service understand the data formats, commands, and protocols to use. Once the contract is in place, the next step is to manage data exchange, whether it is in XML or JSON. For example, a COBOL program might expose its business logic, such as calculating interest rates or processing payroll, as a REST-TFL API, allowing other systems to access it over the internet. This integration not only extends the life of COBOL systems, but also makes them more adaptable to changing business needs. SOAP, or Simple Object Access Protocol, is a protocol that uses XML to structure messages between systems. Unlike REST, which is more flexible and often relies on HTTP methods, SOAP is highly standardized and provides a formal framework for communication. In the context of COBOL, this means that programs can generate WSDL files, which stand for Web Services Description Language. These files describe the available services, their operations, and the data formats they use, making it easier for other systems to interact with them. Implementing SOAP in COBOL involves using XML libraries to create, send, and parse messages. For example, a COBOL application might call a weather service via SOAP by constructing an XML request that includes location data, and then processing the XML response to extract the weather information. This structured approach ensures that even complex interactions are reliable and consistent, making it a popular choice for enterprise-level applications where data integrity is critical. REST-TFL services, on the other hand, use HTTP methods such as GET, POST, PUT, and DELETE to interact with resources. This approach is more straightforward and often results in faster communication compared to SOAP. In COBOL, this means leveraging its strong file handling capabilities to manipulate data, while also using libraries to parse JSON, a format that is widely used in modern web applications. For instance, a COBOL program might make a GET request to a public API like GitHub to retrieve information about a repository. The response, which is typically in JSON, can then be processed using COBOL's data manipulation features. This integration allows COBOL systems to interact with modern platforms, enabling tasks such as fetching real-time data, updating records, or triggering actions based on external events. By embracing rest, COBOL can remain relevant in an environment where simplicity and speed are often prioritized. The practical applications of integrating COBOL with web services are vast. One common scenario is exposing COBOL data through web services to support mobile applications. For example, a banking system written in COBOL might provide an API that allows a mobile app to check account balances or transfer funds. Another use case involves automating batch processing tasks by linking them to real-time web service triggers. Imagine a COBOL program that processes payroll data at the end of the month and automatically sends the results to a cloud-based reporting tool via an API. Integrating with cloud platforms like Oz or Azure further enhances scalability, allowing COBOL systems to handle increased workloads without significant infrastructure changes. Additionally, middleware such as IBM MQ can be used to securely transfer data between systems, ensuring that sensitive information is protected during transmission. These scenarios demonstrate how COBOL can be adapted to meet modern demands while maintaining its core strengths. Security is a critical consideration when integrating COBOL with web services, as these systems often handle sensitive data. Ensuring secure communication is paramount. This involves using HTTPS, which encrypts data in transit, and implementing authentication mechanisms like OAuth or API keys to verify the identity of requesting systems. Input validation is another essential practice, as it prevents malicious data from causing unexpected behavior or vulnerabilities. For example, a COBOL program that processes user inputs must check for SQL injection or other attacks that could compromise the system. Encrypting sensitive data, such as customer information or financial records, during transmission further safeguards against interception. Finally, monitoring and logging API usage helps detect unauthorized access or suspicious activity, ensuring compliance with regulatory requirements. By addressing these security concerns, organizations can confidently extend the capabilities of their COBOL systems while maintaining trust and integrity. To ensure successful integration of COBOL with web services, developers should follow best practices that promote efficiency and maintainability. One key approach is modularizing COBOL code, which involves breaking down programs into smaller, reusable components. This makes it easier to update or adapt sections of the code without disrupting the entire system. Using XML or JSON parsing libraries can also improve performance, as these tools are optimized for handling structured data. Testing web service interactions thoroughly is equally important, as it helps identify and resolve issues before they impact real-world operations. For example, simulating different scenarios, such as network failures or invalid inputs, ensures that the system can handle unexpected conditions. Lastly, documenting service endpoints and data formats is crucial for collaboration and future maintenance. Clear documentation allows other developers to understand how the system works and how to interact with it, reducing the risk of errors and streamlining the integration process. A real-world example of COBOL and web services integration is a bank system connecting to a payment gateway. In this scenario, the bank's COBOL application must define API endpoints that allow external systems, such as the payment gateway, to communicate with it. This involves specifying the data formats, such as JSON or XML, and the operations, like processing transactions or verifying card details. The COBOL system then handles the transaction data, ensuring that it is accurate and meets the required standards. Security is a top priority, so the communication must be encrypted using HTTPS, and the system must validate inputs to prevent fraud. The benefits of this integration include real-time payments, which reduce the need for manual processing and improved customer satisfaction through faster transaction times. However, challenges such as ensuring compatibility with the payment gateway's requirements and validating data formats can complicate the process. Overcoming these hurdles requires careful planning and collaboration between development teams. In conclusion, COBOL's ability to integrate with web services is a testament to its adaptability and enduring relevance. By bridging the gap between legacy systems and modern technologies, COBOL continues to support critical operations in industries that rely on its stability. The key to successful integration lies in addressing security, maintaining modular and well-documented code, and embracing continuous learning to stay updated with evolving technologies. As organizations increasingly adopt cloud computing, automation, and real-time data processing, COBOL's role will only grow more significant. With the right strategies and tools, COBOL can remain a vital component of the digital landscape, proving that even the oldest technologies can find new life in the modern world. COBOL has undergone significant transformation over the years, integrating modern programming paradigms such as object-oriented programming. While traditionally known for its procedural structure, COBOL now supports key OOP features like classes, objects, inheritance, and polymorphism. This evolution allows developers to structure their code in a more modular and reusable manner, bridging the gap between legacy systems and contemporary software practices. By adopting OOP principles, COBOL programs can achieve enhanced organization, making it easier to manage complex applications. This session will delve into the practical application of these concepts, demonstrating how they can be leveraged to improve code efficiency and maintainability in COBOL environments. At the core of object-oriented COBOL are several fundamental concepts that redefine how programs are structured. Classes serve as blueprints for creating objects, defining their attributes and behaviors. For instance, a class might represent a customer, containing data like name and account number, along with methods to process transactions. Objects are specific instances of these classes, each holding unique data while sharing the same structure. Inheritance enables a class to inherit properties and methods from another, promoting code reuse and reducing redundancy. Polymorphism allows methods to be tailored for different classes, enabling flexibility in functionality. Encapsulation ensures that data and methods are bundled within a class, restricting direct access and enhancing security. Together, these principles form the foundation of object-oriented design in COBOL, offering a structured approach to software development. The integration of object-oriented programming in COBOL brings numerous advantages that address modern software challenges. One of the most significant benefits is improved code reusability. Through inheritance, developers can build on existing classes, avoiding the need to rewrite code from scratch. This not only saves time, but also ensures consistency across applications. Maintenance becomes more straightforward as changes can be localized to specific classes, minimizing the risk of unintended side effects. Scalability is also enhanced as modular code structures allow for easier expansion of applications. Additionally, encapsulation fosters better collaboration among teams by defining clear boundaries for data access and functionality, reducing conflicts and improving overall project management. These benefits make object-oriented COBOL a powerful tool for modernizing legacy systems. To implement object-oriented concepts in COBOL, developers must first define classes using the class ID statement. For example, a simple class might be declared as class ID myClass, followed by the definition of its attributes and methods. Once a class is established, objects can be instantiated to represent specific entities, such as a customer or a product. This is achieved through declarations like declare myObjectType myClass, which creates an instance of the class. Inheritance further extends this capability, allowing a class to inherit properties from another. For instance, a child class can inherit from a parent class, adopting its data and methods while adding new features. These practical examples illustrate how COBOL's object-oriented features enable structured and efficient programming, even within the constraints of the language. Despite its advantages, object-oriented COBOL presents several challenges that developers must navigate. One limitation is that COBOL's OOP features are not as comprehensive as those in modern languages like Java or C++. This means that certain advanced OOP concepts may require workarounds or additional coding. Developers must also be proficient in both procedural and object-oriented programming, as many legacy systems still rely on traditional COBOL structures. Additionally, older systems may lack support for full OOP capabilities, necessitating careful planning when modernizing applications. Debugging and testing can also become more complex as the interplay between classes and objects introduces new layers of functionality. However, with proper training and experience, these challenges can be overcome, allowing developers to harness the full potential of object-oriented COBOL. In conclusion, object-oriented COBOL offers a robust framework for enhancing code structure and reusability, making it a valuable asset for modern software development. By leveraging classes, inheritance, polymorphism, and encapsulation, developers can create more organized and maintainable applications. However, it is essential to recognize the limitations of COBOL's OOP features and approach their implementation with careful design. The goal is to balance the strengths of object-oriented programming with the unique characteristics of COBOL, ensuring that legacy systems can be modernized effectively. As you apply these concepts, remember that thoughtful planning and continuous learning are key to achieving success in this evolving landscape. Welcome to this session on advanced file processing in COBOL. Today, we will explore techniques that enhance the efficiency and effectiveness of handling data in large-scale applications. Efficient file management is critical when dealing with vast amounts of data, as it ensures quick access, reduces processing time, and maintains data integrity. By the end of this presentation, you will have a solid understanding of indexed, relative, and dynamic file operations, which are essential for building robust and scalable COBOL programs. Let's begin by diving into the world of indexed files and how they enable direct record access. Indexed files are a cornerstone of efficient data retrieval in COBOL. By using the key clause, we can directly access specific records without scanning the entire file. This is achieved through an index that maps key values to their corresponding record positions. The implementation of indexed file organization involves defining the index structure in the data division and using the indexed clause in the file description. The benefits of indexed files include rapid retrieval, efficient sorting, and seamless updating of records. For example, in a customer database, an indexed file allows you to quickly locate a customer's information using their unique identifier, such as a customer number. This level of performance is indispensable in applications where speed and accuracy are paramount. Relative files offer another approach to file handling, particularly when dealing with fixed-size records. Instead of relying on keys, relative files use relative record numbers to access data directly. This method is ideal for scenarios where records are of uniform size and require random access. In COBOL, the syntax for defining relative files involves the relative clause in the file control section, specifying the record number as the access method. Use cases for relative files include applications like inventory systems, where items are stored in a predictable order, or in situations where sequential or random processing is required. By leveraging relative record numbers, you can optimize both storage and retrieval operations, making this technique a valuable tool in your COBOL arsenal. Dynamic file processing allows for real-time updates, insertions, and deletions within a file, making it essential for applications that require frequent data modifications. The red statement with the update option enables you to retrieve a record and prepare it for modification, while the right statement updates the file with the new data. This approach is particularly useful in transactional systems where data must remain consistent and up to date. However, dynamic processing also introduces challenges such as file locks and concurrency control. When multiple users or processes access the same file simultaneously, it's crucial to implement mechanisms to prevent conflicts, such as locking records during updates or using transaction logs to track changes. Mastering these techniques ensures that your programs handle data dynamically while maintaining reliability. No file processing system is immune to errors, which is why robust error handling and recovery strategies are vital. The file status clause in COBOL provides detailed information about the success or failure of file operations, allowing you to detect issues such as file not found, invalid record numbers, or disk space shortages. Recovery strategies may involve restoring data from backups, reinitializing corrupted files, or implementing retry mechanisms for temporary errors. Logging and debugging are also critical practices, as they help trace the root cause of problems and ensure that your programs can recover gracefully from unexpected failures. By incorporating these practices into your code, you can build systems that are resilient and easy to to maintain. Optimizing file processing is key to reducing I/O overhead and improving overall performance. Techniques such as buffering and record caching can minimize the number of disk accesses by storing frequently used data in memory. Buffering involves temporarily holding data in a memory area before writing it to the file, while caching keeps recently accessed records readily available. Additionally, optimizing access paths, such as using indexes or sequential processing, ensures that data is retrieved efficiently. For large datasets, these optimizations can significantly reduce processing time and resource consumption, making your COBOL programs more scalable and efficient. Always consider the specific requirements of your application when choosing the right optimization strategy. When working with multiple files, combining them through join operations can streamline complex data retrieval tasks. This technique involves merging data from two or more files based on a common field, such as a customer ID or product code. Synchronizing file pointers is essential to ensure that data from different files aligns correctly during processing. For example, in a transaction system, you might need to access a customer file and an order file simultaneously to retrieve a complete record. Managing file dependencies, such as ensuring that one file is updated before another, prevents inconsistencies and ensures data integrity. By mastering multi-file processing strategies, you can handle intricate data relationships with confidence. Let's examine real-world applications to see how these techniques come into play. Consider a customer data processing system that uses indexed files to quickly locate customer records by their unique identifiers. In an inventory management scenario, relative files can efficiently track stock levels by accessing records based on their position in the file. For a banking transaction system, dynamic file processing ensures that account balances are updated in real time, even under heavy load. These examples highlight how advanced file processing techniques address specific challenges in different industries. By applying these methods, you can design systems that are both powerful and adaptable to evolving business needs. Best practices for file handling are essential for creating maintainable and reliable COBOL programs. Always use file status codes to detect and respond to errors during file operations, as this ensures that your programs can handle unexpected situations gracefully. Documenting file structures and access methods is equally important, as it makes it easier for others to understand and modify your code. Testing edge cases such as empty files, invalid input, or unexpected data formats helps identify potential issues before they become problems in production. By following these practices, you can build file handling routines that are robust, efficient, and easy to troubleshoot. In summary, advanced file processing in COBOL encompasses a range of techniques designed to improve efficiency, reliability, and scalability. From indexed and relative files to dynamic processing and error recovery, each method plays a critical role in handling data effectively. As you continue your journey with COBOL, remember that mastering these concepts will enable you to build systems that perform well under demanding conditions. In our next session, we will explore file security and modern integration strategies, expanding your ability to create secure and interoperable applications. Thank you for your attention, and I look forward to our continued exploration of COBOL's capabilities. Distributed systems are collections of independent computers that appear to users as a single coherent system. These systems allow multiple machines to work together, sharing resources like processing power, storage, and data. The key characteristics of distributed systems include scalability, which means they can grow and handle increased workloads, fault tolerance, ensuring the system continues to operate even if some components fail, and resource sharing, which optimizes the use of available hardware and software. COBOL, despite being a legacy language, plays a role in modern distributed environments by integrating with contemporary technologies. Its ability to handle large-scale data processing and its compatibility with mainframe systems make it a valuable tool in distributed architectures where reliability and performance are critical. COBOL has a long history of being used in mainframe systems, where it powered critical applications in industries like banking, government, and healthcare. These systems were centralized, but as technology evolved, COBOL had to adapt to distributed architectures. This adaptation is achieved through integration with middleware, which acts as a bridge between COBOL programs and other systems. For example, COBOL can interact with web services by using APIs to send and receive data over the internet. It can also connect to cloud platforms, allowing legacy COBOL applications to leverage modern infrastructure. This flexibility ensures that COBOL remains relevant in environments where both old and new systems must coexist. In distributed COBOL systems, communication protocols are essential for ensuring data flows smoothly between components. Common protocols include TCP/IP, which provides reliable data transmission over networks, HTTP for web-based interactions, and message queues like IBM MQ, which enable asynchronous communication. COBOL supports network communication through call statements and APIs, allowing programs to interact with external services. However, for systems to communicate effectively, data must be serialized, converted into a format that can be transmitted and reconstructed. This ensures compatibility across different platforms, whether they are using COBOL or other languages. Without proper serialization, data might be misinterpreted or lost during transmission. Integrating COBOL with modern technologies opens new possibilities for legacy systems. For instance, COBOL can expose functionality as REST APIs, enabling it to interact with web applications and mobile devices. This allows businesses to modernize their interfaces without rewriting entire systems. In a microservices architecture, COBOL modules can function as individual services, each responsible for a specific task. This modular approach enhances scalability and makes maintenance easier. Cloud migration strategies for COBOL applications often involve rehosting them in cloud environments, refactoring code to improve efficiency, or using containers to encapsulate COBOL programs. These approaches help organizations leverage cloud benefits like flexibility and cost savings while preserving their existing COBOL investments. Distributed COBOL systems face several challenges. Security is a primary concern, as data transmitted across networks must be protected from unauthorized access. This involves implementing encryption, secure authentication methods, and monitoring for vulnerabilities. Data consistency is another challenge, as maintaining uniform data across multiple nodes requires careful coordination. Techniques like distributed databases or consensus algorithms help ensure all nodes have the same information. Additionally, maintaining maintaining legacy COBOL code in modern infrastructures can be complex. Older systems may use outdated tools or lack documentation, making updates and troubleshooting difficult. Addressing these issues requires a combination of modern practices and deep knowledge of COBOL's architecture. To succeed in distributed environments, COBOL applications should follow best practices. Modular design is crucial as it allows components to be developed, tested, and deployed independently, improving scalability and reusability. Middleware like CICS or WebSphere can facilitate seamless integration with other systems, acting as a bridge between COBOL and modern technologies. Regular testing and monitoring are also essential. Automated testing ensures that changes do not introduce errors, while monitoring tools track performance and detect issues in real time. These practices help maintain the reliability and efficiency of COBOL applications in complex distributed systems. Real-world applications demonstrate COBOL's enduring relevance. In the financial sector, COBOL powers transaction processing systems that handle millions of operations daily, supporting distributed banking networks. In healthcare, legacy COBOL systems interact with modern electronic health record platforms, ensuring patient data is accessible across different facilities. Retailers use COBOL-based inventory management systems to track stock levels across multiple stores, enabling efficient supply chain operations. These examples highlight how COBOL continues to support critical infrastructure, even as newer technologies emerge. By adapting to modern requirements, COBOL remains a vital component of distributed systems. The future of COBOL in distributed systems is shaped by trends like hybrid cloud environments, where legacy and modern systems coexist. COBOL will play a role in maintaining critical infrastructure, such as financial and governmental systems, while organizations adopt newer technologies. This dual approach ensures continuity and minimizes disruption. Additionally, the demand for COBOL skills is growing as companies seek experts to modernize legacy systems. Professionals who understand COBOL and its integration with contemporary tools will be in high demand, making these skills essential for sustaining and evolving distributed systems. COBOL remains relevant in distributed systems through its adaptability and continued use in critical applications. Key takeaways include the importance of integration with modern technologies, ensuring robust security measures, and prioritizing scalability. As organizations navigate the complexities of distributed computing, COBOL's role will continue to evolve. Exploring its potential in new environments offers opportunities to leverage its strengths while addressing modern challenges. By embracing these possibilities, professionals can contribute to the ongoing success of distributed systems that rely on COBOL's reliability and efficiency. Understanding memory allocation in COBOL programs is essential for building efficient and reliable applications. COBOL, as a language designed for business and administrative systems, often deals with large volumes of data, making memory management a critical factor in performance. When a program runs, it requires memory to store variables, data structures, and temporary information. Efficient memory usage ensures that programs execute quickly and do not consume excessive resources, which is particularly important in environments where system resources are limited. The working storage section, linkage section, and file section are the primary areas that influence memory behavior. The working storage section holds variables and data structures specific to a program. The linkage section facilitates data exchange between programs, and the file section manages file I/O operations. By mastering these sections, developers can optimize memory usage and improve overall program efficiency. The working storage section is where most variables and data structures are declared in a COBOL program. It acts as a temporary holding area for data during program execution. However, excessive use of large arrays or redundant variables can lead to memory bloat, which slows down performance and increases the risk of errors. For example, declaring a massive array without a clear purpose can waste memory and complicate debugging. To avoid this, developers should design data structures with specific needs in mind, reusing variables where possible and limiting the scope of data. Additionally, initializing variables is crucial. Uninitialized variables can hold garbage values, leading to unpredictable results. By setting initial values, programmers ensure that data starts in a known state, reducing the likelihood of runtime errors and making the program more robust. The linkage section plays a vital role in passing data between programs or modules, which is common in COBOL systems that rely on modular design. By referencing external data rather than duplicating it, the linkage section helps reduce memory usage and improves data consistency. For instance, if two programs need to share a common dataset, the linkage section allows them to access the same memory location without copying the data. This approach not only saves memory, but also ensures that changes made in one program are immediately visible in another. COBOL provides mechanisms like the address of clause to dynamically access data, enabling programs to handle varying data sizes and structures. This flexibility is especially useful in environments where data requirements change frequently, as it allows programs to adapt without requiring extensive rewrites. The file section and associated buffers are critical for managing file I/O operations in COBOL. Files often contain large amounts of data, and efficient retrieval is key to program performance. Buffers act as temporary storage areas that hold data while it is being read from or written to a file, reducing the number of direct I/O operations. Optimizing buffer sizes can significantly improve speed, as larger buffers reduce the frequency of I/O calls. For example, a buffer that is too small may cause the program to wait frequently for data, while one that is too large may waste memory. The record key clause is another important feature, particularly for indexed files. It allows programs to quickly locate specific records using a key, which is essential for applications that require fast data access. By tuning these elements, developers can ensure that file operations are both efficient and scalable. While COBOL traditionally uses static memory allocation, developers can simulate dynamic behavior using specific constructs. The linkage section, for instance, allows programs to reference external data, mimicking the flexibility of dynamic allocation. The use statement enables programs to access external storage, such as shared memory or files, without duplicating data. Additionally, the move and reference clauses provide tools for manipulating data in memory without allocating new space. For example, using reference to pass a variable's address can allow multiple parts of a program to work with the same data, reducing memory overhead. These techniques are essential for creating adaptable programs that can handle varying data sizes and requirements, even within the constraints of static allocation. Efficiency in COBOL programming often hinges on minimizing unnecessary data movement between memory sections. Moving data between the working storage, linkage, and file sections can be time-consuming and resource-intensive. Instead, developers should structure their code to keep data in the most appropriate section for as long as possible. The perform statement is a powerful tool for this, as it allows loops to be executed without repeating code, improving both readability and performance. For example, a loop that processes multiple records can be defined once and reused, reducing redundancy. Conversely, the copy statement, while useful for reusing code, should be used judiciously. Overusing copy can lead to bloated programs and complicate debugging, as changes to a copied section may affect multiple parts of the code base. One of the most common pitfalls in COBOL programming is failing to initialize variables, which can lead to unpredictable behavior. Uninitialized variables may contain leftover data from previous operations, causing logic errors that are difficult to trace. Another issue is overusing large data structures without proper cleanup. For example, declaring a large array and not resetting it between uses can lead to memory leaks, where the program consumes more memory than necessary. Additionally, neglecting to close files after use can result in resource leaks, where the operating system is unable to release file handles, potentially causing system-wide performance issues. These problems highlight the importance of disciplined coding practices, such as always initializing variables, managing data structures carefully, and ensuring that all resources are properly released when no longer needed. In one case study, a developer reduced memory usage by reusing variables in a payroll processing program. Instead of declaring separate variables for each calculation, they used a single variable and updated its value as needed, significantly lowering the program's memory footprint. Another example involved optimizing file I/O by adjusting buffer sizes. By increasing the buffer size for a transaction processing system, the program's response time improved by 40%, demonstrating the impact of careful tuning. A third case study focused on using the linkage section to share data between two programs. By passing a common dataset through the linkage section, the programs avoided duplicating data, which not only saved memory, but also ensured consistency across the system. These examples illustrate how practical applications of COBOL's memory management features can lead to measurable improvements in performance and reliability. Effective memory management begins with planning during the design phase. Developers should analyze the program's data requirements and allocate memory accordingly, avoiding last-minute decisions that may lead to inefficiencies. Regular code audits are also essential, as they help identify redundant data structures or unnecessary memory usage. For instance, a routine check might reveal that a variable is no longer needed, allowing it to be removed. COBOL's built-in features, such as the search and sort verbs, can further enhance efficiency. Search allows for quick lookups in tables, while sort optimizes data processing by leveraging the language's native capabilities. By combining these tools with disciplined coding practices, developers can create programs that are both efficient and maintainable. In conclusion, effective memory management is a cornerstone of reliable and high-performance COBOL programming. By understanding how memory is allocated and used in the working storage, linkage, and file sections, developers can design programs that run efficiently even under heavy workloads. Prioritizing structured data handling ensures that programs are not only functional, but also scalable and maintainable. Applying these principles to real-world projects means that developers can address challenges like resource constraints and data complexity with confidence. Whether optimizing file I/O, reusing variables, or leveraging COBOL's built-in features, the goal is to create applications that perform well and stand the test of time. Code refactoring is the process of improving existing code without altering its external behavior. This means that while the internal structure or organization of the code changes, the output or functionality remains the same. The primary purpose of refactoring is to enhance readability, making the code easier to understand and maintain. It also improves maintainability by reducing the complexity that can accumulate over time. Additionally, refactoring can boost performance by optimizing inefficient structures or redundant operations. Common scenarios where refactoring is necessary include identifying and eliminating redundant code, clarifying unclear logic that may have been written hastily, and updating outdated structures that no longer align with modern programming standards. The benefits of refactoring are significant, as it simplifies debugging by making the code more predictable, fosters better collaboration among developers by ensuring consistency and reduces technical debt, which is the cost of maintaining poorly written code over time. In COBOL, there are several key refactoring techniques that can be applied to improve code quality. One technique is simplifying complex conditionals by using if-else statements or the evaluate verb, which can replace multiple nested if conditions with a more structured approach. Another technique is removing duplicated code, which can be achieved through the use of copy statements or sections that allow code reuse across different parts of a program. Restructuring nested loops is also essential for clarity, and this can be done by using the perform varying construct to make the loop logic more explicit and manageable. Finally, optimizing data handling involves ensuring that file control and working storage sections are properly structured to handle data efficiently, reducing the risk of errors and improving overall performance. Adhering to best practices in COBOL programming is crucial for writing clean and maintainable code. One fundamental practice is using meaningful variable names that clearly indicate their purpose, such as WS customer name instead of generic names like WS name. Documenting code with comments is equally important, as it helps explain the logic behind complex sections and provides context for exceptions or edge cases. Consistent indentation and spacing ensure that the code's structure is visually clear, making it easier to follow. Additionally, avoiding excessive GOTO statements is vital, as they can lead to unstructured and hard-to-follow code. Instead, structured programming constructs like perform and evaluate should be prioritized to create a logical flow that is easier to debug and maintain. Modularization and reusability are essential for creating scalable and efficient COBOL programs. Breaking large programs into smaller sections or paragraphs allows for better organization and easier testing. Reusable code blocks can be encapsulated in copybooks, which can then be included in multiple programs, reducing redundancy. Leveraging subprograms through the call statement enables modularity by separating distinct functionalities into independent modules. This approach not only improves code organization, but also makes it easier to update or replace specific components without affecting the entire system. Ensuring clear interfaces between modules, such as well-defined input and output parameters is critical for maintaining the integrity and reliability of the overall program. Robust error handling and validation are essential for ensuring the reliability of COBOL applications. Implementing error checking using the file status clause allows developers to detect and respond to file-related issues, such as missing or corrupted data. Validating input data through if conditions helps prevent invalid entries from causing unexpected behavior. Logging errors using display statements or external files provides valuable information for debugging and troubleshooting. It is also important to avoid silent failures, where errors are not explicitly addressed, as this can lead to undetected issues. Instead, developers should prioritize explicit error messages that inform users or administrators of problems, enabling timely resolution. While refactoring can yield significant benefits, it is important to avoid common pitfalls that can undermine its effectiveness. One such pitfall is overcomplicating the code during the refactoring process, which can introduce new bugs or make the code harder to understand. Ignoring legacy code conventions can also be problematic, as it may lead to inconsistencies or conflicts with existing systems. Failing to test the code after refactoring is another critical mistake, as it can result in undetected errors that affect functionality. Lastly, neglecting documentation during restructuring can leave the codebase less accessible to future developers, reducing its long-term maintainability. Real-world refactoring examples demonstrate how these techniques can be applied to improve COBOL programs. For instance, replacing repetitive move statements with a loop can eliminate redundancy and make the code more concise. Converting nested if statements into evaluate blocks can enhance readability by organizing conditions in a structured manner. Extracting a section of code into a separate program allows for reuse and simplifies the main program. Finally, cleaning up unstructured GOTOs by replacing them with perform statements creates a more logical and maintainable flow, reducing the risk of errors. In conclusion, refactoring is a powerful tool for improving code quality and long-term efficiency. It is essential to prioritize readability and maintainability over quick fixes, as these factors directly impact the sustainability of the code base. Adhering to COBOL best practices ensures consistency and reduces the risk of errors. Finally, always testing after refactoring is critical to confirm that the changes do not introduce new issues and that the program continues to function as intended. By following these principles, developers can create more reliable, efficient, and maintainable COBOL applications. COBOL stands for Common Business-Oriented Language and was specifically designed to address the needs of business applications. It emerged in the 1950s as a response to the growing demand for a standardized language that could handle complex data processing tasks across different industries. Despite being over 6 decades old, COBOL remains a cornerstone for many critical systems in finance, government, and healthcare. Its enduring relevance lies in its ability to manage large volumes of data with precision and reliability. Unlike some programming languages that prioritize speed or flexibility, COBOL emphasizes readability, which makes it easier for teams to maintain and update systems over time. This characteristic has made it a vital tool for organizations that rely on stable, long-term solutions for their core operations. Cloud computing represents a transformative approach to delivering computing services, including servers, storage, databases, and software over the internet. This model allows organizations to access resources on demand without the need for physical infrastructure. There are 3 primary models of cloud computing. Infrastructure as a service, which provides virtualized computing resources like servers and storage. Platform as a service, which offers a framework for developers to build and deploy applications. And software as a service, which delivers fully functional software solutions over the web. The benefits of cloud computing are vast, including the ability to scale resources up or down based on need, reduce capital expenditures by shifting to a pay-as-you-go model, and enable remote access to applications and data from anywhere in the world. These advantages have made cloud computing a driving force behind digital transformation in modern businesses. The integration of COBOL with cloud environments has become a strategic priority for organizations seeking to modernize their legacy systems. While COBOL was originally developed for mainframe computers, today's cloud platforms like Oz, Azure, and IBM Cloud provide the tools and infrastructure needed to run COBOL applications in a more flexible and scalable manner. This is achieved through technologies such as containers, which encapsulate COBOL programs along with their dependencies, making them portable across different environments. Virtual machines further enhance this capability by allowing COBOL applications to operate in isolated, secure spaces within the cloud. Tools like Docker and Kubernetes play a crucial role in this process, enabling the deployment, management, and orchestration of COBOL-based systems. By leveraging these modern tools, organizations can preserve their existing COBOL investments while benefiting from the agility and efficiency of the cloud. Migrating COBOL applications to the cloud offers a range of significant advantages that extend the language's utility in today's digital landscape. One key benefit is the ability to retain and build upon existing COBOL code bases, which often represent decades of business logic and critical operations. By integrating these systems with cloud infrastructure, organizations can scale their processing capabilities to handle larger workloads without the need for expensive hardware upgrades. The cloud also facilitates real-time data processing and integration with modern cloud-native applications, allowing COBOL systems to interact seamlessly with newer technologies. Additionally, cloud adoption reduces the costs associated with maintaining physical servers and data centers, while improving system flexibility through automated resource allocation. These factors make the cloud an ideal environment for extending the lifespan and functionality of COBOL-based solutions. Despite the benefits, migrating COBOL applications to the cloud presents several challenges that require careful planning and execution. One major hurdle is the need to refactor legacy COBOL code to ensure compatibility with cloud environments. Many COBOL programs were written for mainframe systems and may not function optimally in a distributed cloud architecture. This process often involves rewriting or re-architecting parts of the code base to align with cloud-native principles. Another challenge is addressing security and compliance concerns, as moving sensitive data to the cloud requires robust encryption, access controls, and adherence to regulatory standards. Finally, there is a growing demand for professionals who possess expertise in both COBOL and cloud technologies, as the intersection of these fields is still relatively niche. Overcoming these challenges requires a combination of technical skill, strategic investment, and ongoing training to bridge the gap between between legacy systems and modern cloud platforms. The future of COBOL in the cloud hinges on its ability to adapt to evolving technological landscapes while maintaining its core strengths. Modernization strategies such as containerization, microservices, and hybrid cloud solutions are proving essential in extending the relevance of COBOL for new applications. By integrating COBOL with cloud frameworks, organizations can leverage its reliability and data handling capabilities alongside the scalability and innovation of cloud computing. This synergy not only preserves valuable legacy systems, but also opens up opportunities for enhanced performance and faster development cycles. As businesses continue to embrace digital transformation, the adaptability of COBOL to cloud environments will be critical in ensuring its continued use in sectors where stability and precision are paramount. The journey of COBOL into the cloud is not just about preservation. It is about evolution, ensuring that this foundational language remains a vital part of the technology ecosystem for years to come. Debugging is a critical skill for any COBOL programmer, especially when dealing with legacy systems that form the backbone of many critical business operations. Understanding why debugging matters goes beyond just fixing errors. It ensures the reliability and performance of applications that may handle millions of transactions daily. Common challenges include tracing logic through nested loops, identifying issues in large code bases, and interpreting cryptic error messages that may not directly point to the root cause. To tackle these, advanced tools and techniques are essential. These include leveraging compiler diagnostics, using step-by-step execution, and integrating modern debugging practices into traditional COBOL workflows. By mastering these, you can significantly reduce downtime and improve the overall quality of your code. COBOL provides several built-in tools to aid in debugging. The display statement is a fundamental tool for outputting variable values and program states in real time, allowing you to track how data changes as the program runs. The trace option offers a way to execute your code step by step, giving you control over the flow and helping you pinpoint where things deviate from expectations. Additionally, compiler diagnostics and runtime error messages are invaluable. These messages often highlight syntax issues, data type mismatches, or logical errors. but interpreting them requires a deep understanding of COBOL's structure. By combining these tools, you can systematically isolate and resolve issues without relying on external utilities. Beyond the built-in tools, third-party debugging utilities offer advanced features that can streamline the debugging process. Tools like Micro Focus Debugger and IBM Debug Tool provide functionalities such as breakpoints, which let you pause execution at specific lines of code and watch windows that monitor variable values dynamically. Memory inspection capabilities allow you to examine the state of your program's memory, which is crucial for identifying issues like buffer overflows or uninitialized variables. These utilities often integrate seamlessly with COBOL development environments, providing a unified interface for code editing, testing, and debugging. This integration can save significant time, especially when working on complex applications with multiple modules. Advanced debugging techniques require a strategic approach. Placing display statements judiciously can help track variables across different sections of your code, but overuse may clutter the output. Conditional breakpoints are a powerful alternative, allowing you to pause execution only when specific conditions are met, which is especially useful for isolating rare or intermittent issues. Analyzing dumps and core files, which capture the program's state at the time of a crash, can reveal insights into runtime anomalies. These files often contain detailed information about memory, registers, and call stacks, making them essential for diagnosing critical failures. Combining these techniques with systematic testing ensures a thorough approach to problem solving. For long-running processes, logging and tracing are indispensable. Implementing a logging framework allows you to record program behavior continuously, providing a historical record of events that can be reviewed later. Using write statements to log key operations, such as the entry and exit of subroutines or changes in critical variables, helps trace the program's flow. Parsing these logs requires attention to detail, as patterns in errors or performance bottlenecks can emerge over time. Tools like log analyzers or custom scripts can automate this process, making it easier to identify recurring issues. Effective logging turns a chaotic debugging scenario into a structured investigation. Debugging in COBOL often involves overcoming common pitfalls, Misusing the GO to statement can lead to spaghetti code, where the program's flow becomes tangled and difficult to follow. To avoid this, structure your code with clear control structures like perform and exit. Off by one errors in loops or arrays are another frequent issue, often caused by incorrect index ranges or boundary conditions. Thorough testing and boundary checks can mitigate these. Data type mismatches and overflow issues arise when values exceed the capacity of their declared data types, leading to unexpected results. Using data validation and proper scaling techniques ensures that your program handles all possible inputs gracefully. Adopting best practices can transform your debugging process. Modularizing your code by breaking it into smaller, self-contained modules makes it easier to isolate and test individual components. Version control systems like Git allow you to track changes over time, making it simple to revert to a stable version if a new bug is introduced. Collaborating with peers through code reviews and pair programming brings fresh perspectives to problem solving, helping catch issues that might be overlooked by a single developer. These practices, when combined, create a robust workflow that minimizes errors and accelerates resolution. In summary, mastering advanced debugging tools and techniques is essential for any COBOL programmer. The combination of built-in features like display and trace with third-party utilities provides a comprehensive toolkit for troubleshooting. By applying best practices such as modular coding and version control, you can significantly improve your efficiency. Remember, debugging is not just about fixing errors. It's about understanding your code deeply and continuously refining your skills. With consistent practice and thorough documentation, you'll become more proficient in navigating the complexities of COBOL applications. COBOL remains a critical language in modern industries, particularly in banking, government systems, and legacy infrastructure. Many financial institutions still rely on COBOL for core transaction processing, and government agencies use it for critical data management. Understanding COBOL is not just about learning an old language, but about mastering tools that power essential services. By applying COBOL skills to real-world scenarios, you bridge the gap between theoretical knowledge and practical problem solving. This session will guide you through the entire life cycle of COBOL projects, from building applications to testing and deploying them in real environments. We will explore how to translate classroom concepts into functional, industry-ready solutions. Defining the project scope is the first step in any successful COBOL initiative. This involves identifying requirements, setting clear deliverables, and aligning with business goals. Organizing code into modules such as input, processing, and output ensures that your programs are structured, manageable, and scalable. For example, separating input handling from data processing allows for easier debugging and updates. Version control systems like Git are essential for tracking changes, collaborating with teams, and maintaining a history of your code. These practices not only streamline development, but also reduce the risk of errors during complex project iterations. Adhering to COBOL syntax and structure standards is fundamental to writing reliable code. Consistent formatting and naming conventions improve readability and facilitate collaboration. Modular programming enhances reusability, allowing you to create self-contained components that can be tested and maintained independently. For instance, a module for data validation can be reused across multiple applications. Comments and documentation are equally vital. They serve as a roadmap for future developers, explaining the purpose of code segments and the logic behind complex operations. This practice ensures that your work remains accessible and understandable over time. Developing test cases for both routine operations and edge scenarios is crucial for identifying potential failures. Edge cases, such as invalid input or unexpected data formats, can expose hidden flaws in your code. Debugging tools like the IBM debug tool provide a structured way to trace logic errors, step through code, and inspect variables in real time. Unit testing focuses on individual components, ensuring they function as intended, while integration testing verifies how these components interact. Together, these strategies build confidence in your application's reliability and reduce the likelihood of critical errors in production. Preparing deployment scripts is a key step in transitioning COBOL applications to live environments. These scripts automate tasks such as compiling code, configuring settings, and transferring files to mainframe or legacy systems. Ensuring compatibility with existing infrastructure requires careful planning, including matching data formats, system dependencies, and security protocols. Long-term maintenance involves regular updates, patching vulnerabilities, and adapting to evolving business needs. By anticipating these requirements, you create applications that not only meet current demands, but also remain resilient to future challenges. To summarize, this session has covered the essential steps of real-world COBOL projects: planning, coding, testing, and deployment. Each phase requires attention to detail, adherence to best practices, and a focus on practical outcomes. Real-world projects offer invaluable experience, helping you develop skills that are directly applicable to industry roles. I encourage you to engage with sample projects, experiment with different scenarios, and refine your understanding through hands-on practice. By doing so, you will build a strong foundation for a career in COBOL development and contribute to the ongoing legacy of this enduring programming language. Welcome to today's session on advanced COBOL programming. We begin by revisiting the fundamentals of COBOL to ensure a solid foundation before delving into more intricate topics. This review will reinforce key concepts such as data types, control structures, and basic file operations. Our primary focus will shift towards advanced techniques that address real-world scenarios. By the end of this training, you will have enhanced your coding skills to write more efficient and robust programs. You will also gain the ability to debug complex applications and optimize their performance to meet modern demands. Let us embark on this journey to elevate your COBOL expertise. In this section, we explore advanced file handling techniques that are essential for managing large and dynamic data sets. Sequential access is ideal for processing records in the order they are stored, while indexed access allows for faster retrieval using key fields. Direct access, on the other hand, enables random retrieval of records based on their physical location. The rewrite and delete statements are powerful tools for modifying or removing records dynamically, which is critical in applications requiring real-time data updates. Additionally, understanding file status codes is vital for preventing errors. These codes provide insights into the success or failure of file operations, allowing you to implement proactive error handling mechanisms. Mastering these techniques ensures reliable and efficient data management in COBOL applications. Complex data structures in COBOL allow for the manipulation of multidimensional data and large datasets. Arrays, defined using the OCCURS clause, enable the storage of multiple instances of a data item, making them ideal for scenarios such as inventory management or statistical analysis. Nested tables, where one table is embedded within another, add another layer of complexity, requiring careful planning to maintain data integrity. Dynamic memory allocation further enhances flexibility by allowing programs to adjust memory usage based on runtime conditions. To efficiently handle these structures, the search and sort verbs are indispensable. The search verb facilitates quick lookups within tables, while the sort verb organizes data in a specified order, improving processing efficiency. These techniques are crucial for handling large-scale data operations in COBOL. Effective error handling and debugging are critical in COBOL programming to ensure program reliability. The error interrupt paragraph allows you to intercept runtime exceptions, providing a structured way to handle unexpected errors. Interpreting file status codes and I/O error messages is essential for diagnosing issues, as these codes often indicate specific problems, such as file not found or invalid data. Debugging tools like Trace, Display, and COBOL debuggers are invaluable for tracing program execution and identifying logical errors. The trace statement provides a step-by-step view of program flow, while the display statement outputs variable values for inspection. COBOL debuggers offer advanced features for setting breakpoints and inspecting memory. By leveraging these tools, you can systematically resolve issues and improve program stability. Performance optimization is a key aspect of writing efficient COBOL programs. Minimizing I/O operations through buffering and caching reduces the overhead of disk access, which is particularly important in high-volume transaction systems. Efficient use of indexes and key fields in indexed files accelerates data retrieval, ensuring that applications respond quickly to user requests. Additionally, optimizing loops and conditionals can significantly reduce computational overhead. For example, avoiding nested loops where possible, or using optimized conditional logic can improve execution speed. These strategies not only enhance performance, but also contribute to the scalability of COBOL applications in modern environments. Integrating COBOL with modern systems is essential for leveraging legacy code in contemporary architectures. COBOL programs can be called from Java or .NET applications using APIs or web services, enabling seamless interaction between different technologies. Embedding SQL within COBOL allows direct database access, simplifying data manipulation and reducing the need for external tools. Data conversion techniques, such as transforming legacy data formats into modern standards like XML or JSON, ensure compatibility with newer systems. These integrations bridge the gap between traditional COBOL applications and modern software ecosystems, allowing organizations to maintain and evolve their systems effectively. Working with legacy, COBOL code presents unique challenges, particularly in maintaining readability and functionality. Legacy systems often lack documentation, making it difficult to understand complex logic. Debugging nested loops and recursive programs requires careful analysis to identify logical errors that may not be immediately apparent. Compatibility issues with newer COBOL standards, such as COBOL 2014, can also arise due to changes in syntax or features. Addressing these challenges involves adopting best practices, such as refactoring code for clarity, using version control to track changes, and staying updated with industry standards. By tackling these issues proactively, you can ensure that legacy systems remain viable and maintainable. As an advanced COBOL programmer, adhering to best practices is crucial for writing clean, maintainable code. Modular programming, using sections and paragraphs, allows you to break down complex programs into manageable components, improving readability and reusability. Comprehensive documentation, including comments and flowcharts, ensures that others can understand and modify your code effectively. Regular code reviews and version control practices, such as using Git, help identify potential issues early and maintain a history of changes. These practices not only enhance collaboration, but also ensure that your COBOL applications remain robust and adaptable to future requirements. In conclusion, mastering advanced COBOL concepts is essential for building reliable and efficient systems. As you apply these techniques, remember that continuous practice and adaptation to modern tools are critical for long-term success. By staying updated with industry trends and refining your skills, you will gain the confidence to tackle even the most complex COBOL challenges. Let this training serve as a foundation for your ongoing journey in COBOL programming, empowering you to contribute effectively to both legacy and modern systems. And just like that, our dreamy coding adventure has come to an end. I hope the gentle ebb and flow of the tutorial, combined with the tranquil melodies, have left you feeling both informed and at ease. Whether you managed to catch every line of code or drifted off into a peaceful slumber, remember that the world of COBOL will always be here waiting for you. Keep your code clean, your mind open, and your spirit relaxed. Don't forget to subscribe to Code Snooze so you never miss out on another soothing coding journey. Hit that like button if this video brought you a moment of calm and learning, and share it with fellow coders or anyone in need of a serene study session. Thank you for joining me in this cozy corner of the internet. Until next time, may your code run smoothly and your dreams be filled with brilliant algorithms. Sweet dreams, sleepy coders.